Good evening, everyone. So, is audio video clear for all? Okay, right. Okay, right. In the last class, we complete the first two ideal properties. What are the first two ideal properties? First one is operation of transformer with finite permeability. Actually, it is infinite permeability, but infinite not possible. So, we taken finite permeability. There we have derived EMF equation of transformer, and then we have seen some observations and some numericals on that EMF equation related. And then second ideal property is what? Operation of transformer with iron loss. Because in ideal, iron loss is what? Zero. But practically that is not possible. So there will be a small amount of iron loss. So that is we considered. And based on that overall no load current, we have the sum of magnetizing current and iron loss current. Okay. So we have seen that phasor diagrams, no load case and load operation total. Now we will go to the third ideal property. What is the third ideal property? Resistance of winding is zero. But practically, is it possible zero resistance? No. For each and every conductor, we have some small resistance. So we are using copper winding, therefore it will have a low resistance, less than 1 ohm mostly. In all these windings, transformer windings, induction, motor windings, synchronous machine, armature winding, these are all will have resistance less than 1 ohm. Low resistance we prefer. Okay. Now, before that, let's see one small numerical. Then we will see the third ideal property. See the question. Read the question. For a specified input voltage and frequency, if the equivalent radius of core of a transformer is reduced by half, the factor by which number of turns in primary should change to maintain same no load current. First of all, what is no load current? No load current, sum of two currents. I naught equal to I mu plus IW. Okay. No load current is the sum of two currents, magnetizing current and iron loss current. But in the question, no load current to be remain same given, which is sum of two currents, but they did not mention anything about iron loss here. So directly it is not possible to solve because we have to consider assumption here. The assumption is the iron loss is zero. Assume iron loss is zero here. Iron loss is zero. Otherwise, exactly we cannot solve this question. Iron loss is zero, then only we can able to solve this. If iron loss zero, then what is the corresponding IW term? Zero. As iron loss is we assuming zero, no iron loss in the transformer core, the corresponding current IW zero. That means the no load current is equal to magnetizing current itself. Okay. No load current is equal to magnetizing current itself. Now, what is the question? For a specified input voltage and frequency, means voltage, there is some voltage and there is some frequency from the source. So this voltage and frequency are the constant, fixed. For a specified means fixed voltage and frequency. If the equivalent radius of core of a transformer is reduced by half. So this is there is a transformer core, square core, cross section is square core it is, and equivalent radius of that core is reduced by half. Equivalent radius of core is reduced by half. Now limb size will reduce. Limb size will reduce. Okay. Now how many turns required? The factor by which number of turns in primary should change to maintain same current. Current should be same. Actually, if you reduce the size of the core, what happened? Size of the core you are reducing. Then what is the flux density? Actual flux density is what? Proportional to flux per unit area. No? Okay. Now you are reducing radius by half. Then size of the core also reduced by half. Radius is reduced, then area will change based on area. So approximately I'm saying whenever radius is reduced, size will reduce. When size reduced, area little reduce. Then what is the flux density? Will increase. Will increase. But it should not happen because for a specified voltage and frequency they given. That means what? V1 by F is what? Constant. Means flux density should remain same. It should not change. Flux density should remain same. It should not change. So accordingly, how many turns should be there now in the winding so that the no load current is remains same? So simple question only, not difficult. Only the assumption we have to make in this question, that is iron loss should be 0. Otherwise, we cannot solve directly. Okay, iron loss 0 taken, IW 0. So I naught equal to I mu itself. I naught is I mu itself. Now, previously we written yesterday's class I mu. What is I mu? V1 by J X naught only. No? From yesterday's equivalent circuit under no load condition, magnetizing current we can find by supply voltage divided by the inductive reactance of that coil Jx naught. Okay, this is equal to V1 by Jx naught is what? Inductive reactance. In inductive reactance, what is the formula for inductive reactance? XL equal to omega L, and capacitive reactance XC is 1 by omega C. Okay, now we are using this inductive reactance formula, omega L. Omega L. Omega means in terms of frequency we can write 2 pi f. 2 pi f into L, inductance. Okay, 2 pi f into L. So here I mu is proportional to V1 constant, because for a specified voltage and frequency, V1 is constant, that is not changing. Frequency also not changing. 2 pi anyhow constant value. Then what is the only variable in this? L. Inductance may vary. Inductance may change. That depends on number of turns, permeability, area. Because what is the formula for inductance? If you remember in first class, I think we have seen inductance formula is what? L equal to, tell me, what is inductance formula? Number of turns N1 square divided by reluctance. So did you remember this? Self-inductance and mutual inductance we derived previously. So self-inductance formula. And what is the reluctance formula separately? L equal to N1 square. Reluctance is L by mu A. Okay. Length, mean length by permeability and cross-sectional area. So L equal to N1 square into mu into A by L. Okay. Now, from this relation, I mu is proportional to 1 by L. I mu is proportional to 1 by L. Now, you can apply this relation here. N1 square mu A by L. Now, which one will change here? Which one will change? As radius is reduced by half. Radius is reduced by half. So, area of cross section will change. Is the length will change? No. Mean length remains same. Length of the core remains same. No change in the length. Only the area will change. So, here we need to find number of turns. Permeability will not change. Same core, that is same material. Length also will not change. Length also will not change. So L proportional to N1 square into A. L proportional to N1 square into A. Number of turns, square of the turns, and area of cross section. So if you write here 1 by N1 square into A. Okay. So L proportional to N1 square A. So that is we taken in the denominator, 1 by N1 square A. Now what is the question? We need same no load current. The no load current should remain same. It should not change. That means I mu should remain same or not? Yes. The I mu should be same indirectly. No load current same is magnetizing current should also be same. Now this I mu should be same 1 by N1 square into here. So this magnetizing current should remain same. That means if you cross multiply, N1 square into A should be constant or not? When I mu is same, when the magnetizing current will be same. If the product N1 square A is constant, I mu also constant, no change in that. So this is should be constant. Now we are applying the formula N1 square. What is the cross sectional area of the core? Cross section area of the core. Pi r square, no? Because see, if you take a square core, observe here. If you take a square core, and when you place one turn here, one turn, if you place on this, what is the form it is coming? If you place one turn on the core, what is the shape of that one turn? Circular or square? That is a circular cross section only, no? The turn will make one circular cross section there, not square cross section. Because if you even if you place on the square core also, the winding will not take exactly square. It is approximately like a circular shape only. Like this only windings will come, number of turns on this. It won't form. Okay, so it is a circular form. So we need to find how many turns required, if this is actually radius, previously radius of core. Now this radius of core is reduced by half. Then number of turns, how many required? So that our magnetizing current is remains same. So that is we are calculating. So A is pi r square. This must be constant. N1 square. Anyhow, pi is constant. R square equal to constant. Now square N1 into R. So anyhow it is constant. N1 into R should be constant. N1 R whole square equal to constant. Constant, no, that's why square is removing. Only N1 R directly I'm taking. Now applying here. In the question, the radius of core is reduced by half. So if you reduce the radius by half, what should be the number of turns so that the product remains same? I mu remains same if the product of this N1 into R remains same. Therefore, if radius is half, you need to double the number of turns so that the value is remains constant. Okay. If the radius is reduced by half, the number of turns should be double so that the product N1 into R remains constant, then I mu also remains constant. I mu constant means no load current also constant. That is only the question. Okay, the answer is option C. The number of turns should be double. Yes, in this core loss is not mentioned. Core loss is not mentioned because they given in the question to maintain the same no load current. That's it. And we know no load current is sum of two currents, magnetizing current and iron loss current. So if you consider iron loss current also, we cannot solve this question. We cannot solve because iron loss variation if given, we should consider that IW also na here. But that is not mentioned in the question. Only when you neglect that core loss in transformer, then only we can able to solve. Otherwise, we cannot solve directly. Okay, that's why we taken iron loss is negligible, neglected. Otherwise, two variations will come. I mu is V1 by Jx naught. And what is IW? V1 by R naught. V1 by R naught. Is R naught depends on any number of turns? No. That is the no load resistance R naught component is there, whatever. That is does not depends on any number of turns. Inductance depends on number of turns. That's why we are neglecting that IW term. Okay. Let's see the third ideal property. Third ideal property is resistance of winding is 0. Yes, you can consider. Yes, if nothing is mentioned, so based on the question, we need to solve. So that will come automatically because how to proceed with the question, you will get only after knowing all information about transformer. Maybe now it is just starting, no? Maybe you'll get doubt how to take, when to take zero, when we should not take zero. All these doubts will come. But after completion of some more topics, you will get some idea on transformer first. Okay. So no need to fear of these questions. Easily we can solve. Okay, don't fear of this. Right. Studying operation of transformer, operation of transformer with resistance of winding, with resistance of winding, operation of transformer with resistance of winding. So actual zero resistance. Ideal case is what? Resistance of winding is zero, but practically zero resistance are not possible. Okay. Yes. So other way also you can consider assuming flux constant, right? Okay. Same no load current means flux should be constant there. Then only I mu constant, IW also fixed. So flux is constant. Yes, right. Now considering transformer, check the figure. Now the total primary winding will have a resistance R1. So I'm considering the total resistance of primary as R1. Total resistance R1 and total secondary resistance R2. Total secondary resistance considering as R2. Let the primary current is I1, secondary current is I2. Now, first of all, the resistance of these windings will comes under which category? So if you go to electrical measurement subject, there we have resistance calculation, inductance calculation, capacitance calculation separately. So there in resistance calculation, you will see we have mainly three types of resistance. What are that? Low resistance, medium resistance, high resistance. Low resistance means the resistance value is less than 1 ohm, and medium resistance less than almost 1 kilo ohm. Up to 1 kilo ohm we consider as medium resistance, and high resistance is greater than 1 kilo ohm. Now for different ranges, we have different methods available to find resistance accurately. For all methods, one method is not suitable. Suppose for all these ranges, one method is not suitable exactly. Like that, for low resistance calculation, which method is suitable? Maybe if you know, you can guess. For low resistance calculation, the best method is Kelvin's double bridge method. Kelvin's double bridge. So this method we use to find the resistance of this transformer windings, because transformer windings will come under low resistance category. So if you want to find this R1, R2 value, you need to conduct this Kelvin's double bridge test. It will give accurate readings for low resistance. Okay, then you can mark R1 is 0.1 ohm, R2 is some 0.2 ohm, like that. Suppose if they given R1 is 0.1, R2 is some 0.2 ohm. Now tell me here, Which winding is high voltage and which winding is low voltage? Primary, secondary. Primary is low voltage or high voltage? You know now already. High voltage, high resistance. Which winding will have high resistance? HV winding. HV winding will have high resistance. LV winding will have low resistance. 0.1 ohm, it is 0.2 ohm. So secondary here indicates HV, primary indicates LV, like that. This is LV winding, this is HV winding. Based on resistance, you can directly consider. No need to see number of turns. If you know the values of resistance, primary resistance and secondary resistance, directly also you can tell this is LV winding, this is HV winding. You no need to see the number of turns or voltage ratings. Okay, this is one method. And for medium resistance, now what are the example for low resistance? Transformer winding resistance, induction motor winding resistance, synchronous machine armature winding, only armature winding, and DC machine armature winding. These are having low resistance, and remaining field windings we have, particularly in generators, DC generator, synchronous generator. That field windings will have medium resistance in the range 100 ohms, 200 ohms, 300 ohms, like that. Okay. So medium resistance example is field winding resistance. Examples, field winding resistance. So which method suitable for medium resistance calculation? Wheatstone bridge. Wheatstone bridge, or we have volt ammeter method. Volt ammeter method or volt ampere method. Okay. For calculation of medium resistance, these two are suitable. And high resistance. What is example for high resistance? All insulating materials. Insulating materials will have a resistance very high in the mega ohms. So these are all comes under high resistance category. What is the method suitable for calculation of high resistance? Megger device. We have one instrument, Megger. Using Megger device, we can find the high resistance calculation. And one more also there, that is loss of charge method, LOC, loss of charge. Maybe you will get in measurements all this. Okay, just I'm giving brief idea how to find resistance. Here also you need to calculate transformer primary winding resistance, secondary winding resistance. But in the lab experiments, what they will do is, in OC test or short circuit test of transformer, we need these resistance values for calculation of losses and all. But they don't do these small experiments finding resistance, Kelvin's double bridge. That they will give some value, take R1 is this much and R2 is this much and do the calculation. That's it. But we should do this experiment also in the lab in the OC and SC test, particularly to find the losses. Okay. Using Kelvin's double bridge, we can find this. Okay, anyhow. So we taken resistance of primary, resistance of secondary, resistance of primary, secondary, R1, R2. Now, what is the problem of considering resistance of winding? Yes, two problems will come, two drawbacks. They are, whenever there is a current flowing through the windings, primary and secondary, there is a voltage drop on primary, voltage drop I1, R1, some voltage will drop in that. Next, a copper loss I1 square R1, a loss also will take place. Similarly, on secondary side, there is a voltage drop on secondary I2 R2 plus there is a copper loss I2 square R2. Okay, due to resistance in transformer windings, a small voltage drop and a copper loss will take place. Now, due to these two, voltage drop and copper loss. So whenever voltage drop takes place, it is a drawback only, no? Just like transmission line also you can consider sending and receiving end. If sending end voltage is 400, what is the receiving end voltage? Do you get same 400 at the receiving end? No, some voltage will drop. Okay, that is we are calculating as a voltage regulation in the lines. Same we will do in transformer also, voltage regulation. Now whenever there is a loss, copper loss, some power is lost or not? Yes, due to this some efficiency of transformer reduces. Efficiency will reduce. So first write 2 points below the diagram. Right. When resistance of winding, when resistance of windings is considered, it will cause a voltage drop. It will cause a voltage drop and copper loss copper loss in the transformer. Copper loss in the transformer, which reduce the efficiency of transformer, which reduce the efficiency of transformer. Okay, which reduce the efficiency of transformer. So this is drawback. Ideal case, zero resistance, so efficiency is good, but here some efficiency reduces. Okay, anyhow, we need to find the voltage drop in transformer and copper loss in transformer. How to calculate that? So observe the figure. In order to find voltage drop and copper loss, you need to find primary current, primary resistance, secondary current, secondary resistance. Now, transformer is having two different electrical circuits or not? Yes. Primary is one circuit, secondary is one circuit, both isolated but magnetically coupled. Both isolated but magnetically coupled they are. Okay, magnetically coupled. So if it is required to find voltage drop and copper loss, what you have to do? You need to solve two circuits. You need to find primary current, primary resistance, secondary current, secondary resistance. So it will be lengthy. Primary calculation separately, secondary calculation separately. So what we do here is, in order to reduce the complexity of this calculation, to reduce the calculations, what we do is we will transfer one resistance to other side. Any one resistance. Secondary resistance you can transfer to primary, or primary resistance you can transfer to secondary. So if you transfer this secondary resistance to primary, then you no need to find the secondary current. No need to touch secondary circuit now. Only primary we solve, enough. We will get total voltage drop and we will get total copper loss. So only single circuit we need to solve. No need to solve two different circuits. For that reason, we need to transfer the resistance from one side to other side based on our requirement. Any side you can transfer. But can you transfer directly the R2 here? Suppose previously I given example, no, R1 is 0.1, R2 is 0.2 ohm, for example. Okay, R2 is 0.2 ohms. And what is the currents on primary and secondary generally? Either for step up or step down transformer, currents are different only now. Low voltage means high current. Let us take the I1 value is some 100 ampere. I2 value is 10 ampere. For example, just example I'm giving. I1 is 100, I2 is 10. Now, if you find individually, you will get some copper loss. Now, what I said, in order to reduce the calculations, we need to convert two circuits into single circuit. For that reason, we need to transfer any one resistance. Suppose I am transferring R2 to primary. Then if you put that R2 here, same value if you place, what is that R2? 0.2. Then is it correct? No. Same resistance you should not place. You should change that value before placing. How to change? Yes, we have to change with a condition here. Because why we need to change is, observe. Secondary set. Before transferring, what is the copper loss on secondary? I2 square R2. Tell me. I2 square R2. I2 means 10. 10 square is 100. 100 into 0.2. So this is 20 watts. Copper loss on secondary 20 watts. Now what is the copper loss on primary? Similarly, I1 square R1. 100 square 10,000 into 0.1. So this is 1000 watts. Okay. 1000. Now what is total copper loss? 1020 watts. Primary copper loss plus secondary copper loss, 1020 watts total. Now if you transfer this R2 directly here, then same current I1 is going in both resistors. No, then we have I1 square R1 plus I1 square R2. Then I1 square R1 is remains same, 1000 watts plus I1 square into R2. Then how much you will get here? 10,000 into 0.2 is 2000 watts. Now how much it is total? 3000 watts. Then is it right? What is the total copper loss previously? Just 1020. 20 here, 1000 here. If you add separately 1020, we are getting. But now 3000. So this is wrong. This is wrong. So you should not transfer directly. Then what is the condition to transfer? Even if you transfer the resistance from one side to other side, the copper loss in the transformer should be remain same. The copper loss in that resistor should remain same. What is the copper loss previously in R2? 20. After transferring to primary, now also it should be 20 only. It should not change. So this condition we utilize. Okay. Because some people will ask doubt. So why R2 is directly not placed here? Why it is changing to some other R2 dash? We will change to R2 dash, some other value. Because if you don't change, this is the problem. Now only I given no total loss is 3000 we are getting. So that is not correct. Loss in transformer should not change. Whatever the changes you do in this. Okay. So keep this figure as it is. Don't change it. Is so write one statement here. Write one statement. It is required to transfer the resistance. It is required to transfer the resistances from one side to other side, from one side to other side. What is the need to transfer? Why we are transferring one side to other? Primary to secondary you can transfer. So you will see what is these words. Okay, you will see now. Primary to secondary you can transfer, or secondary to primary also you can transfer. Why we are transferring? To make two circuits into single circuit, so that our calculation becomes simple. Okay, one side to other side to make a single electrical circuit, a single electrical circuit. Okay, right. Next line. The condition to transfer the resistance is, the condition to transfer the resistance, to transfer the resistance is the copper loss in the resistor, the copper loss in the resistor should be same, before and after transfer, before and after transfer. Okay, now you will understand what we are doing. Before and after transfer means. So completed up to this. Why we should transfer? I will just, what is the reason we are transferring? To make single circuit. Now I will show you clearly which circuits here. Okay, all your doubts will be clear. See now. See now. Now first I will consider secondary resistance I am transferring to primary. Secondary resistance I am transferring to primary. See, side secondary to primary transfer. Secondary to primary transfer. Now see the circuit, secondary to primary. First, uh, secondary resistance I am transferring to primary side. Now the circuit, equivalent circuit will become like this. Already there is R1 on primary side. Okay, as it is I am drawing that R1. Now the secondary resistance I am taking on primary side, transferring to primary side. Now I will put that value here, but not same value. I need to change that. R1 is same as it is, but R2 I need to change. So I am taking it is as R2 dash. Now secondary side, no resistance. Secondary side we don't have any resistance now. No resistance on secondary, only primary side, because we transferred the secondary resistance to primary side. Now is it required to solve two different circuit? No, because total resistance is on primary. So once you know the primary current I1, now you can find total copper loss directly. I1 square R1 plus I1 square R2 dash. Now that R2 dash is how much? That is we need to calculate. Observe here. What is the condition to transfer? Copper loss in the resistor should be same before transfer and after transfer. Before transfer means R2 is secondary side. R2 is on secondary side before it is. Now, what is the copper loss before transferring in that I2 square R2? Okay. Now, after transferring to primary, what is the current flowing in R2? That is R2 dash. What is the current flowing? I1. Now, the copper loss in the same resistor is I1 square R2 dash. So, these two values should remain same. Okay, got it now? The two values, copper loss before transferring, copper loss after transferring should be same. Now, what is R2 dash? Check. R2 dash equal to R2 into I2 by I1 whole square. So this is R2 dash equal to R2 into, what is I2 by I1 in terms of transformation ratio? We know that K equal to N2 by N1 or E2 by E1, or in terms of current it is I1 by I2 approximately. Okay, I1 by I2. So I2 by I1 means 1 by K. So total it is 1 by K whole square, 1 by K square. So the value of R2 dash is R2 by K square. This is the new value of resistance. Now that resistance you need to place here. You will get same copper loss, whatever is there in the original transformer figure. This is separately. If you find I1 square R1 plus I2 square R2, whatever you got, suppose 1020, now also you will get 1020 with this calculation. Okay. Now clear all of you why we need to transfer the resistance. Now do you require to find I2 here? Not required. Only one circuit we will solve enough just by calculating that resistance. Okay. Voltage drop also same. Voltage drop also you will get same, not only copper loss. Yes, we have to place parallel lines. We have to place that lines we have to place. But anyhow, every time we no need to draw here in these diagrams. We have to place these two lines. Okay. Now, therefore, in this diagram, what is the total resistance referred to primary? Total resistance refer to primary. Refer to primary. So we indicate it is as R01. Total resistance refer to primary. R01. What is the total resistance here? R1 plus R2 dash. This is R1 plus R2 dash means R2 by K square. So simple. When you transfer any resistance from secondary to primary, divide that value with K square. Divide that value with K square. That's it. Okay. This is secondary to primary transfer. In the same way, now again we will take primary to secondary transfer. Let's see that. Completed. Made of single circuit is what? Calculation reduced, no? Now you no need to find I2 value. Without that calculation is reduced. Otherwise, you need to solve primary circuit separately, secondary circuit separately. Okay. Calculation will reduce. That's it. Hmm. R naught is separate. Don't combine that R naught, because R naught is not a physical resistance. It is not related with winding. That is completely representing core loss. That's it. R naught is separate. R naught is not having with winding relation. R naught is separate. R naught X naught are separate. So don't combine now. That is complete done. Yes. Next, primary to secondary transfer. Primary resistance transferring to secondary side. Primary to secondary transfer. Primary resistance transferring to secondary side now. Now what is the new value there? If it is transferring to secondary, new value is dash. So the circuit is this. Total resistance. Primary resistance is R1. That is I am transferring to secondary side now. Now no resistance will be there on primary side. You should not take any resistance because that is transferring to secondary. There is already R2 here. Now R1 will come here with a different value. That's why we call R1 dash. I1, I2. Already there is R2. Now R1 is transferring to secondary. It will become R1 dash. R1 dash. So this is the circuit for this heading. Total resistance referred to secondary it is. Total resistance referred to secondary side. Anywhere you can transfer, same answer you will get. Same answer you will get if you transfer to primary or if you transfer to second. Okay. Now what is the condition? Before transferring R1, what is the copper loss in that R1? I1 square R1. Before transferring, R1 is on primary, no? Then I1 square R1 is the copper loss in that. Now if you transfer R1 to secondary, that is becoming R1 dash. Now what is the current flowing in this? I2. Then copper loss is I2 square R1 dash. So after transferring to secondary, the copper loss is I2 square R1 dash. These two values should be remain same. These two should remain same. Accordingly, we find what is the new resistance. So the R1 dash value will be R1 into I1 by I2 whole square. What is I1 by I2 in terms of transformation ratio? K directly. R1 into K square. So what you observe, when you transfer the resistance from primary to secondary, multiply with K square. Multiply that R1 with K square. And if you transfer secondary resistance to primary, divide that value with K square previously. Dividing with K square here. And if you transfer to secondary, multiply. Okay. Now, therefore, total resistance refer to secondary. That is we indicate as R02. R01 means total resistance referred to primary. R02 means referred to secondary. What is the total resistance here? R2 plus R1 dash. Therefore, R02 equal to R2 plus R1 dash means K square R1. Okay. Yes. If 1:1 transformer is there, then secondary resistance directly you can take, because 1:1 means already both having same resistance indirectly. Both windings having same resistance. Okay. Then if it is on primary or if it is on secondary, there is no change. Same answer will be there. Yes. Directly you can transfer that. See, you need to draw every time. We are not drawing. Why this is also you people are asking. Whether it is drawing or not, that is not matter here. You need to draw actually, but generally we are not drawing every time. No, whether it is drawing or not, you should take care. Okay. Currents are not same. Yes, that's why only R1 we are changing to R1 dash. R1 is changing to R1 dash, so that resistance changing here. That's why loss is equal. Whether currents are different, also resistance different. Accordingly, resistance we are changing. That is the condition we are utilizing to find new resistance. Okay. Now, in most of the questions of efficiency calculation and voltage regulation and copper loss calculations, there is some important relations. So write that relations. Hmm. Voltage drop is not directly same. Per unit voltage drops we take. So just wait for some time. Your doubts will clear. See now, make a note. Note. So resistance drop on primary. So all this terminology you have to remember. Don't forget. Resistance drop on primary. What is resistance drop on primary? I1 R1. Okay. This is resistance drop in volts. Voltage drop is in volts only. Now we need per unit resistance drop on primary. Per unit resistance drop on primary. Per unit. So maybe those who are in second year, you people maybe not aware of this per unit system, per unit quantities. So up to you complete the power system, in the power system subject, you will get per unit quantity separately, one chapter. So there you will come to know about all clearly what is per unit and all. Per unit means no units here. We will express everything in units. That is per unit value without any units. So you will see clearly per unit is definition is what? Actual value for anything, current or voltage or anything, actual value by base value. Per unit means actual value by base. Both should be in same units. So those who are not aware of this per unit, you remember here for right now, you will get in power system clearly about all this. Okay. Per unit resistance drop on primary means resistance drop on primary is I1 R1. Actual value it is voltage drop divided by base. What is the primary voltage? On the nameplate we have E1 by E2 now voltage ratings. So this is our primary voltage, that is itself base voltage. So that divided by E1 will give per unit resistance drop on primary. This is in volts divided by this is also voltage. So no units for this. Some value you will get. That's it. Some 0.1 per unit or 0.2 per unit in that. Okay. Next, per unit resistance drop on primary. And if it is required to find percentage resistance drop on primary, percentage resistance drop on primary, how to find percentage resistance? To the same per unit value, multiply with 100, you will get percentage resistance. Okay, percentage resistance drop on primary, it is equation. In the same way, resistance drop on secondary, resistance drop on secondary, resistance drop or voltage drop on secondary. That is nothing but I to R2. I to R2. Now, what is the per unit resistance drop on secondary? Per unit resistance drop on secondary. Nothing but I to R2. Secondary side rated voltage is what? E2. Now that base voltage you have to take E2. And if it is percentage, multiply with 100. Okay. Next, total resistance drop. Total resistance drop refer to primary. Refer to primary. Total resistance drop refer to primary. What is the total resistance refer to primary? How much? R01. Then what is the current flowing in that I1 primary side total? So I1 R01 is total resistance drop divided by this is only resistance drop I1 R01. That's it. Now per unit total per unit resistance drop refer to primary. Refer to primary. How much it is? Per unit, no? That's why same voltage drop you write I1 R01 by E1 primary voltage. In the same way for secondary side. Okay. So just keep in mind these relations. Again, we use in the losses. Okay. Per unit resistance drop refer to primary side. I1 R01 total per unit resistance drop refer to primary. Nothing but I1 R01 by E1. So this per unit resistance drop will be same on primary and secondary, but not direct voltage drops. Not direct voltage drops. Okay. I1 R1 is different. I2 R2 is different because currents and resistance are different. Now their voltage drops will be different on both sides. And if you transfer the resistance to one side, what is the total resistance drop? I1 R01. Or if you transfer the resistance totally to secondary side, what is the total voltage drop? I2 R02. And if you find the per unit resistance drop on both sides, you will get the same answer. Okay. Those who are in second year about per unit quantities or per unit system, maybe you don't know clearly why we go with per unit values is to make calculation very easy. Generally voltages, currents, powers, these are all big values now. 11 kV, 33 kV, or 10 ampere, 100 ampere voltages, powers and all. So with big numericals, calculation will be difficult. But if you convert the same into per unit, uh, in per unit system, rated current, suppose rated current normally in units is 100 amperes. Rated current is 100 amperes, primary side. Now same rated current in per unit, you can write as 1 per unit. That's it. Same 100 amperes in per unit system, you can write as 1 per unit. Rated it is. Like that voltage is 400 volts. The same voltage in per unit system, you can consider as 1 per unit rated voltage. Like that in per unit, we will deal with small numericals, 0 point, that is 1 per unit or 0.5 per unit, like this, small numericals. So due to that, calculation will become very easy in per unit system. That's why we go to per units. Okay, anyhow, you will get clearly about this per unit system in the power system subject. There you will see. So meanwhile, remember these equations enough. Percentage resistance drop on primary. So similarly, percentage resistance drop. So right below this, one more line. Percentage resistance drop. Percentage resistance drop refer to primary. Refer to primary. What is this equation? Refer to primary means total resistance. I1 R01 by E1. This is per unit into 100 percentage it is. Similarly, percentage resistance drop refer to secondary. Refer to secondary. Now, total resistance referred to secondary is what? R02. And what is the secondary current? I2. So, I2 R02 by E2 into 100. So, this is percentage resistance drop referred to secondary. So, see, all these calculations required in efficiency and voltage regulation. Okay, up to now, you don't get all this. So, remember these equations in efficiency, voltage regulation, particularly we use this. Okay. And let's see a small numerical, how we get numerical on these calculations. See this. Assuming an ideal transformer, the Thevenin's equivalent voltage and impedance as seen from the terminals X and Y means from the secondary side, or with respect to secondary side, what are the equivalent voltage and impedance. So still we have not talked about reactance, that will come in the fourth one, leakage flux. So there we will consider X1 X2 on primary also. Okay, so impedance or reactance or resistance, same calculation you will get. Whatever you have seen for resistance, same formulas. Transferring to secondary, multiply with k square. Transferring to primary, multiply with divide with k square. So same you will get for all resistor, reactance, impedance. Okay, apply the same formula here also. See, primary side, let this is Z1 is 1 ohm, and this is let V1 sine omega t, sine omega t. Now what we have to find? The equivalent voltage and impedance as seen from X and Y, means with respect to this secondary side, what is the new voltage, what is the voltage, and what is the impedance. If you transfer to secondary, it will become V2 and Z2. What is that values? Now tell me, when you transfer the impedance to secondary side, impedance, resistance, reactance, same. Okay, when you transfer impedance to secondary, what we have to do? We have to multiply with k square. What is k here? There is 1:2 number of turns. K we can find easily. K equal to n2 by n1. See, sometimes they will give in the question voltage rating some 200 by 100 volts, 200 by 100 volts, for example. So there also this is E1 by E2. Now you can find K using this also. If it is not given, they given here number of turns ratio given. So using that you can find. So 1:2, n2 is 2, n1 is 1. So 2 by 1, K value is 2. So if you transfer the impedance to secondary side, it will become Z1 dash. What is Z1 dash? Multiplying Z1 into K square, no? Okay, multiply here. Z1 is 1, K is 2 square. This is equal to 4 ohms. So impedance we got first. Next, voltage. Primary voltage is this. Primary voltage is V1, this is. And how to find secondary voltage? Simple. We have E2 by E1 equal to N2 by N1. Okay. V2, E2 by E1 equal to N2 by N1. So you can consider this V2 by V1. So you can consider E1 or E2 anything. V2 by V1 equal to N2 by N1. What is N2 by N1? 2. Then what is V2? V2 equal to 2 into V1. What is V1 here? Sine omega t. So 2 sine omega t. V2 is 2 sine omega t. Okay. So the voltage and impedance refer to secondary. Voltage is 2 sine omega t and impedance is 4 ohms, which is option A. Yes, right. Yes, voltage also you can transfer. Voltage transferring means already there is turns ratio. If you know one voltage, other voltage you can find. So it is not actually transferring, calculating secondary voltage if you know primary voltage. That's it. Or if you know secondary voltage but not primary, you can find primary voltage. So these are all RMS voltages, RMS, not instantaneous. For all these voltages, directly we take magnitudes. Okay, angles we don't take. Next up, see the next one. Fourth ideal property. Actually, what is the fourth ideal property? Leakage flux in transformer is zero, but zero leakage flux not possible practically. So we will consider that. Right. So heading operation of transformer, operation of transformer with leakage flux, with leakage flux. Actually, it is zero leakage flux, but zero not possible. Now, again up to previous diagram, same I am drawing the transformer circuit figure. Same figure I am drawing again. So step by step, we are building the complete terms of transformer. So previously what we have here, R1 is there on primary. Okay, so same I am taking. Total resistance of primary indicated as R1. R1 and total secondary resistance indicated as R2. Let the total secondary resistance is R2. And primary current is I1, secondary current I2. Okay, now observe. Practically, we have some flux leakage. Now tell me, leakage flux is present in primary winding, secondary winding, both primary and secondary. What is answer? Leakage flux is present in primary, comma, in secondary, or in both primary and secondary. Leakage flux is, yes, right. Okay, enough. Yes. Leakage flux will be there in both primary and secondary, not only in primary. Now, suppose they given the question under no load condition, the leakage flux is present in which of the winding? Primary, secondary, both. Yes, only in primary, because under no load, secondary is open. No, only for primary we are giving supply. Only for primary we are giving supply. Therefore, there is a current flux production. So in that some flux will be leakage. No current on secondary because open, secondary no load. So no flux present produced by secondary winding and there is no leakage at that time. So under no load condition, the leakage flux is only on primary side. But under load operations, leakage flux will be there on both primary and secondary. Now tell me one more point. This leakage flux is variable flux or constant flux? This leakage flux is variable or constant? Yes, this is a variable flux. But what is flux in the core? The flux in the core is constant flux, but not leakage flux. Leakage flux is the variable flux in transformer. Why variable? Because load on transformer is a constant load or variable loads. Load on transformer means you take your home, in your home itself the electrical apply all appliances. So that is itself load. So in your home, do you have same load that is continuously you are having, you are switching on all the loads 24 hours? No. Based on the time in the night or evening times after 6 o'clock, definitely we will on the lights. Means then load increases. But during daytime, only motoring loads will be there. Motoring loads will be there, but not lighting loads. Very, very less we use. So like that, load is fluctuating. Whenever load is changing on transformer, secondary current will change. When secondary current will change, primary will also automatically change. So whenever currents in windings changes, the flux produced by the windings will change. So leakage fluxes also changes. So remember, the leakage flux in transformer is present in both primary and secondary under load operation, and this leakage flux is variable, which depends on the load of transformer. Okay, so if you want to write that point, the leakage flux, the leakage flux is present. The leakage flux is present in both primary and secondary windings. The leakage flux is present in both primary and secondary windings under under load operation, under load operation, and this is a variable flux, and this is a variable flux which depends on the load of transformers, which depends on the load of transformers, which depends on the load of transformers. Okay, now let us considering, due to primary current, a small amount of flux is leakage, a small amount of flux leakage on primary. So this is phi L1, leakage flux on primary side. And due to secondary current, whenever current is flowing on secondary, a flux phi 2 is produced. In load operation also we have seen flux phi 2 on secondary side. In the total flux, some small amount of flux will be leakage. Leakage flux means what? The flux which links with only one winding, but not both windings. Both windings means that is useful flux or main flux. So this is leakage flux on primary and leakage flux on secondary. So whatever flux is flowing in the core, that flux is balanced by both primary and secondary flux. Primary flux, secondary flux, both compensating now under load operation. So they are compensated each other. But is the leakage flux is compensated? No. The leakage flux on primary different, leakage flux on secondary different. This is also one important point. Remember, leakage flux is variable and leakage flux present on both the sides, primary and secondary, and the magnitude of leakage flux is different on primary and also on secondary. Not same it is. This is phi L1, this is phi L2. So leakage flux is different on primary and secondary. Why different? Because currents are different now. As currents are different, flux produced is different, and overall flux we are talking complete flux is different. So due to that, leakage also will be changed slightly. So leakage flux is not same on primary and secondary. Remember that point. Now observe, due to the flux present in the core here, whatever the flux is passing in the core, that flux is causing an EMF on primary winding E1 and an EMF on secondary winding E2. Okay, that is we know already. EMF will induce in two windings. Now additionally, Now additionally, this leakage flux is linking with only primary winding. This leakage flux is linking with only primary winding. This leakage flux will cause an additional EMF on primary, let EX1. This leakage flux will cause additional EMF on primary, EX1, and secondary side, the leakage flux will cause an additional EMF induced in the secondary winding, let EX2. But are you taking this EX1 into your rating, voltage rating of transformer? Suppose if you observe nameplate, suppose we have some 400 volts by 200 volts. What is this 400? Primary induced EMF, and this 200 secondary induced EMF, and this is due to main flux or useful flux only they will give, but they don't give this EX1, this EX2. That EX1 additional EMF induced no due to leakage flux on both primary and secondary side. So this EX1 and this EX2 is not represented in the voltage rating. Now this EX1, this EX2 we will consider as a voltage additionally induced, that is due to inductive reactance. Why it is? We will represent this voltage with I1 X1 inductive reactance, and secondary side I2 X2 inductive reactance I2 X2, and primary side I1 X1. Why we are representing this voltage with a inductive reactance? This is due to, it is the EMF due to leakage flux, which is a reactive component. Flux related any drop or any voltage is always what? Reactive only, no? Previously, this is due to resistance of winding directly. So I1 R1 drop and I2 R2 drop on secondary. Now, due to leakage flux on primary and secondary windings, some voltage is drop or not, because 400 only you are indicating. Actually, there is some plus voltage, no? Additional voltage also there, some 5 volts or 4 volts due to that leakage flux, but that is not included. That is the voltage drop for us. Okay, you are considering only that 400 volts according to nameplate, and this small voltage due to leakage flux is not considering. That is, we are considering as a voltage drop in transformer. And how to represent that voltage drop? This voltage drop we are representing using inductive reactance on both primary and secondary windings. That's why we will consider for every coil resistance and reactance. Not only here, for induction motor also, and synchronous generators also, motors also. So in induction motor also you will see stator winding having resistance R1 and reactance X1, and rotor winding resistance R2, reactance X2. So for every winding which is having in the nature of coil, so every winding is coils only, no? Number of turns will be there. So that is having resistance, reactance. Okay, write one point here. Right. Right. In practical, a small amount of flux, a small amount of flux will be leakage, will be leakage on both primary and secondary windings, on both primary and secondary windings, which depends on the load of transformer, the load of transformer. The drop due to leakage flux, because if there is no leakage flux, some more EMF will be there in the rating or not? Yes. If there is no leakage flux, total flux is in the core itself, then due to that more EMF will induce, that will be there on the nameplate, but that is not there due to leakage flux. Whatever EMF is there, that is not indicating. So that is we are considering as voltage drop in the respective windings. So how to represent that voltage drop? As a inductive reactance. So write that. The drop due to leakage flux. The drop due to leakage flux is represented as an inductive reactance drop. An inductive reactance drop on both primary and secondary. On both primary and secondary. So that is I1X1 drop on primary and I2X2 drop on secondary side. So take these points. Why not capacitive? This is electromagnetic energy. Already I said in previous classes also. Why we are representing with inductive reactors? Due to magnetic energy here. For static energy only, we go with capacitor. No, direction of leakage flux is not necessary. That is a drop. No, drop. Why it is drop? Why it is representing as drop? Actually, if there is no leakage flux, total EMF induced in the winding is 400 volts. Okay, but due to some flux leakage, the flux present in the core, passing in the core, linking the both windings is reduced little. So little EMF reduced. So 390 only. Now what happens to the 10 volts drop? In the form of what drop? Leakage flux drop. So that is representing as this inductive reactance drop due to magnetic energy. It is not capacitive reactance. Okay. Now considering on both the sides, inductive reactance X1 on primary and X2 on secondary. So from now, every time whenever we draw this circuit, transformer circuits, every time we draw primary side resistance reactance, secondary side resistance reactance. Okay. Now, like previous resistance transferring from one side to other, reactance also we need to transfer. Same reactance also we need to transfer. Now tell me one important point here. Due to inductive reactance, is there any I square X losses? We have I square R losses, copper loss we call. And due to this inductor and capacitor, do you have any power loss? No, there is no power loss here. Due to inductors, there is no power loss. So we don't have these I1 square X1 losses. Do you have this one? Have you seen anywhere it is? No. Only I square R losses we have, but not loss due to inductor and capacitor. They are just energy storing elements. So due to this inductor and capacitor, we have only voltage drop. What is the primary voltage drop? I1 X1. And what is the secondary voltage drop? I2 X2. Now, if it is required to transfer the reactance from one side to other side, just like resistance, what is the condition we have to use? What is the condition we utilize for resistor? Copper loss in the resistor should be same before transferring, after transferring. But now for inductive reactors, what is the condition to be used? Yes, only voltage drop condition we have to use. And that condition also per unit voltage drop, not direct voltage drops. Not direct voltage drops. Per unit voltage drop in reactants on primary and secondary should be same before and after transferring. Okay, first write the condition, then in the equation you will see what it is. Yes, per unit drop is same in transformer. So why it is same, everything you will see in per unit quantities, because here it is not possible to show. It is again so much lengthy concept again to show the per unit system right here. In order to transfer, in order to transfer the reactants from one side to another side, from one side to another side, the condition is, the condition is the condition is per unit reactants drop, per unit reactants drop should be same, should be same before and after transferring, before and after transferring. Same condition you can apply for resistance also. Remember this point. This same condition, per unit reactance drop we are calling, no? Reactance drop or voltage drop, these are all same. So we call sometimes per unit resistance drop or per unit voltage drop on primary. Anything same only. All these words are same. Per unit resistance drop on primary, or per unit voltage drop on primary, or per unit reactance drop on primary, or per unit reactance voltage drop on primary. Anything same only. Okay, don't confuse in this. Same condition you can apply for resistor also. Same answers you will get. Okay, first. Secondary to primary transfer. Secondary reactants transferring to primary side. Same answer, same relations. Whatever you got for resistor, same for reactants also you will get. Okay, no need to confuse and while remembering these equations. Both are same, simple. Right here. Secondary to primary means I am transferring now this secondary reactance X2. This secondary reactance X2 to primary side here. X2 to primary side here. Then if you directly transfer, values will change, drops will change. So in order to have same per unit reactance drop, the condition is what? Before and after transferring, the per unit reactance drop should be same in that. So for that reason, applying here, before transferring, what is the per unit reactance drop on secondary? Same as resistors. Per unit reactance drop on secondary. What is that? I2 X2 by E2. This is called per unit reactance drop. Per unit reactance drop. Okay. I2 X2 by E2. Now, if you transfer to primary, X2 will become X2 dash. And primary side, what is current? I1. And primary side, what is voltage? E1. So primary side current is I1. X2 will change to X2 dash and primary voltage E1. So these two should be same. Per unit reactance drop should be same. That's it. Now calculate X2 dash from this. X2 dash equal to X2 into I2 by I1 into E1 by E2. Okay, just cross multiply because X2 dash value required for us. How much to be replaced there? Now, what is this? X2 dash equal to X2 into I2 by I1 is 1 by K. E1 by E2 also 1 by K. So total 1 by K square. Same as it is resistor values you will get. If you transfer resistance from secondary to primary, what we have to do? Divide with K square. Now same for reactance also. Divide with K square. Okay, same relations you will get. The only condition we use different. If we use this condition for resistor, you will get the same answers only. Okay. For resistor, two conditions you can use because in resistor we have voltage drop and also loss. Any condition you can use. Then what is the circuit? If you draw the circuit for this, primary side R1, X1, now X2. X2 only I'm transferring. So I'm not writing about resistance here. R1, X1, X2 dash. Now secondary side we have only R2. Now this R2 also if you transfer to primary, no? If you transfer to primary, R2 will become R2 dash. Then nothing will be there on secondary side. Total terms will be on primary side only. Okay. So this is the circuit for this. Therefore, total reactance refer to primary. How we write refer to primary means total reactance refer to primary. How we represent x01 just like r01. This is x1 plus x2 dash, where x2 dash is x2 by k square. Okay, complete up to this first. You can apply total reactive power absorbed, but calculation is again lengthy, no? Reactive power equations and all you have to write. Shiva, under no load condition, leakage flux only on primary, no? Because if it is no load case, under no load, is there any current on primary? Supply giving to primary side, for example, secondary no load condition. We are not connecting anything here. Then there is a primary current. What is that? Only I naught. Is there any current on secondary? No current. This current is zero because open it is. Then is there any flux produced due to secondary here? No flux is produced. Only due to primary a flux is produced. The same flux is flowing in the core. And here only there is some leakage flux. But because this flux is going in the core, it is. Secondary winding is not producing any flux. Okay. So no leakage flux there. So leakage flux is only on primary side. Clear? Reactance drop is more. Reactance drop only more. Not only here, in every AC machine, reactance drop only the greater compared to resistance drop. Okay. So this is a secondary to primary transfer. In the same way, right? Primary to secondary transfer. Primary to secondary transfer. Now, same condition. Per unit reactance drop before transferring, after transferring should be equal. Now, before transferring on primary, what is per unit reactance drop? I1 X1 by E1 on primary. Now, if you transfer X1 to secondary side, what we have? Secondary current, and X1 will become X1 dash, secondary voltage E2. Both should be same. Per unit reactance drop should be same before and after. Now, if you calculate from this, X1 into E2 by E1 into I1 by I2. So what it is, X1 dash equal to X1 into E2 by E1 is K, I1 by I2 is also K. Totally it is X1 K square. Just multiply the X1 value with K square, then we get X1 dash. That's it. Therefore, total per unit reactance drop. Reactance drop refer to primary. Refer to primary equal to I1 X01 by E1. Or if you write refer to secondary, total per unit reactance drop. Reactance drop refer to secondary. Refer to secondary equal to I2 X02 by E2. So if you calculate these two values, whatever you will get this answer, this value also same. Both are equal. You will get same answers for this. Both are equal. Per unit reactance drop, whether you find respect to primary or with respect to secondary, both values will be same. For resistance, previous one, you can take to any condition. Same condition you can take. Which condition? Now for reactance, whatever we taken now, per unit resistance drop should be same before and after transfer. You can use that, or you can use copper loss in the resistor should be same before and after transfer. We have utilized the copper loss there. You can use this condition, whatever we use for reactance, same condition for resistor also. You will get same, because for resistor, two chances are there. Voltage drop is there in resistor, copper loss also there, I square R loss. But for reactors, we have only voltage drops. That's why we use this condition here. Okay. Okay. So with this four ideal properties, we complete. Four ideal properties. What are the first property? Ideal property. Permeability is infinite. Second, iron loss is zero. Third, resistance of winding zero. Fourth, leakage flux is zero. Now, what is the fifth one? The shape of BH curve is linear, but practically it is non-linear. Now, only this point we are not seeing right now. After completion of some more topics, at the last, before three-phase transformer, we will see this point. Okay, right now this is not required for us. So there, before starting three-phase transformer, we will see about this. Okay, no? Now, right side heading, equivalent circuit of transformer. All right, exact equivalent circuit of transformer. Up to this equivalent circuit, whatever we are drawing in equivalent circuit, it is same for induction motor also. Same. If you know well about equivalent circuit, you got already induction motor equivalent circuit. Both are same. Exact equivalent circuit of transformer. Exact equivalent circuit of transformer. You people may get doubt. Previously we have drawn equivalent circuit. Now what it is? Yes, previously we have drawn which circuit that is? Which circuit that is? That is equivalent circuit up to no load condition we have drawn. But there we don't have any R1, X1, any R2, X2. Only no load we have drawn. That is not complete circuit. Now this is the complete circuit of transformer. So this circuit is only important in the tests. Mostly we use these circuits only. OC test and SC test. Brother figure. See, primary side resistance R1, reactance X1, and no load branch R0 X0. And secondary side we have resistance reactance R2 X2, and load is connected to secondary. And primary side supply voltage is this V1, resistance R1 X1, R0 X0, IW, I mu, and I naught, I1 dash, and this is I1 total primary current. And the EMF induced on primary is this E1, here E2, this is E2, I2, R2, X2, and terminal voltage we get V2 across load. This is our load, and you should indicate here with a dotted line. This is ideal transformer. Inside the dotted line, ideal it is. This is ideal transformer. Otherwise, if you don't write the two lines, no need to write all this. Okay. This is exact equivalent circuit of transformer. Yes. No lines. No need to draw that lines. But if you draw, no, you should indicate with the dotted lines as ideal. This part is ideal. And if you take combinedly, this is practical, then you should remove the two lines. Okay. If you know concept enough, whether you are drawing or not, if you know, that is enough. Now, one question to all of you. Listen. If you draw, what is this branch we call? No load branch it is. R0, X0 we call no load branch. I have drawn this branch after R1, X1. Then is it right? Or if you draw, let us remove here, remove that here, and draw the same no load branch here. Draw the same no load branch before R1, X1. Now, which one is correct? Drawing before is correct or drawing after is correct? Drawing this no load branch before R1, X1 is right, or after R1, X1 only right? Actually, both looks the same. No problem. I1 is sum of no load current and I1 dash satisfying. Okay, enough. Yes, good. After only correct, not before. Okay, enough. After only correct, not before. You should not draw before. After only right. This is only correct. Why it is observe. If you draw before R1, X1, suppose first after, if you draw after R1, X1, now I0 is flowing here, I0 is flowing in R1, I0 also flowing in X1, because under no load operation, under no load, what is the current drawn by transformer? Only no load current, okay, only I0. Now due to I0, a small copper loss will take place or not? Or a small voltage drop due to resistance will take place or not? Yes, because that is flowing in winding now. Transformer winding, it is flowing. So due to that small no load current, there will be a small copper loss, and there will be a small voltage drop due to resistance and reactance. So overall we call impedance drop, it is I naught Z1. So if you draw after R1, X1, then I naught is flowing in R1, X1 also. Otherwise, if you draw here, then I naught will not go in R1, X1. If you draw before R1, X1, no, I naught is directly going without passing through R1, X1. That means no load impedance drop will not take place, and no load copper loss also will not take place. So this is not exact. This is just approximate. Exact means after R1, X1 only correct. Okay. This is exact circuit. Remember, drawing after R1, X1 only, the exact circuit of transformer. Now we will go to, this is, here we have two circuits, no? Two circuits we have. Now what we do is, we will make this complete circuit a single circuit. This is primary circuit and this is secondary circuit. Now, if I ask to find I1, you need to calculate I2, you need to calculate I0, I1 dash, and then I1. So this is lengthy calculation. then what we can do is, no need to solve two different circuit. We can solve only one circuit. How? Transfer all secondary parameters to primary side. Transfer R2 to primary, transfer X2 to primary. Then if you transfer, it will become a single circuit. Okay, so write that heading. Equivalent circuit refer to primary. Equivalent circuit refer to primary. Refer to primary. Brother circuit. So primary side already we have R1, X1, and no load branch R0, X0. And now R2, X2, I am transferring to primary. What is the value will become? R2 will become R2 dash. X2 will become X2 dash. So the new values you have to write here. R2 dash, X2 dash. And load also we are transferring to primary. Suppose if load having some impedance now previously in the previous figure, if load having some impedance ZL, then what ZL will become? ZL dash. Same, whatever the formula is there for R2, X2, same for ZL also. Okay, this is load impedance I1. Now we have made a single circuit. So calculation is simple. I1, R1, X1. We no need to solve two different circuit. I mu, IW, I0. This is I1 dash and R2 dash, X2 dash, and the voltage across this is V2 dash. V2 dash. What is V2 dash? V2 dash equal to V2 by K. So V2 by V1 equal to N2 by N1, or E2 by E1 equal to N2 by N1. No, that's why V2 dash will be V2 by K. And if load having impedance ZL, now ZL will become ZL dash. What is ZL dash? ZL by K square. R2 dash, R2 by K square. X2 dash, X2 by K square. Now it is a single circuit. Single circuit it is. Okay. This is also exact circuit. Exact circuit refer to primary. Yes, it's a small internet problem. So it is okay. Now visible for all of you. Yes, okay, right. Okay, check one more time. Hmm. So whatever voltage is there on secondary, if you transfer to primary, it will be divided with K, because what is the voltages and current relation with K? So E2 by E1 equal to K, or approximately also you can take V2 by V1 also K only, or N2 by N1 also K only. Okay, N2 by N1 equal to K. Now if you observe here, secondary side voltage is V2. Now if you transfer that voltage to primary, what is the new voltage? So we know V2 by V1 equal to N2 by N1. Okay, this is equal to K. If you transfer secondary voltage to primary side, means primary side voltage required, then what it is? V1 equal to V2 by K. Now what is the primary voltage? V1 equal to V2 by K. With respect to secondary voltage V2 we know, but we need primary side voltage. Then if you transfer that is to primary, in terms of primary, V1 is V2 by K. Okay, in calculation of numericals, your all doubts will be clear. Now don't think very much. All your doubts will be cleared in the numericals. Okay, and who is asking this? Oh, Harshavardhan. Why LV turns is more? Where is LV in this figure? Which is LV? So did I say LV winding or HV winding in this? No, no. Hmm. So don't see figures. Maybe here I don't know which is LV, which is HV, anything. So based on the number of turns, primary looks HV, more number of turns, secondary is LV. Okay. Now we will go to approximate circuit. Okay. After completion of this approximate circuit, we will take break. Hmm? See this. This is exact circuit only. This is exact circuit. Now to find I1, there is little difficult for us. Why difficult? Suppose I said to calculate I1 value. Then what is I1? It is vector addition of I1 dash plus I naught. This is now to find that I1 dash and I naught, you need this node voltage or not. See this voltage V1 we know, supply voltage is we know, but this node voltage you need to calculate. Let this voltage is some Vx. You know, we need to find that voltage first. Then you will get I1 dash. So you should be aware now, all of you, network theory, how to find voltages, currents from different networks. So if you know this node voltage, I1 dash easily you can find Vx by this total impedance. And I naught also now you can find by calculating IW, IMU separately. So it will take some time or not. You need to apply nodal analysis and then find Vx and then find I1 dash and then I naught. So it is taking time, but in order to reduce this complexity and to make calculation little faster, what we can do, let's move this no load branch before R1 X1. Let us shift that no load branch before R1 X1. Then if you shift before R1 X1, is it exact circuit? No. Now that will be a approximate circuit. So that approximate circuits only we utilize in all our calculations, because approximate means small variations will be there for true value and calculated value, but not very big variations. Because what is the value of no load current compared to load current? Very small, 4 to 5%, like that. Small current it is. So that won't create big variation in our calculation. That's why we are shifting this no load branch before R1 X1. Okay, that is our first approximate circuit. Right. Right. Setting approximate circuits. Approximate circuit. Approximate circuit. So up to this complete approximate circuit, everything same for induction motor. Right. Setting first approximate circuit. We have two approximate circuit. First one, first approximate circuit. Now what we do in the first approximate circuit is shifting or moving the no load branch before R1 X1. So write that point. Moving or shifting the no load branch, before R1 X1, before R1 X1. So before R1 X1, we will draw that no load branch now. Now the circuit is like this. R1 X1, R2 dash, X2 dash, and here load. Okay, this one R1 now R0 X0 we are drawing before R1 X1. Now observe one more simplification we get here. One more simplification. This is R1 X1, R2 dash, X2 dash. This is I1 dash, I0. Now R1 R2 dash in series, R1 plus R2 dash. What is R1 plus R2 dash? Previously we written R01, total resistance referred to primary, R01. Now X1 X2 also in series, X1 plus X2 dash, directly you can add that. Then totally X01 it is, and here R0 X0 V1. Now the same circuit I am redrawing with a small simplification like this. Total resistance I am taking as R01 and total reactance I am taking as X01. Now it is a very small circuit. No? It looks very small compared to this one. Both are same. Both are same. After little simplification, we are writing this R01 here, X01, I1, I0, I1 dash, R0, X0. Okay. Now calculation is simple or not? Then now in this figure, is it required to apply any nodal analysis? Do you need to find this voltage Vx? This node voltage is required to find? No, because this is also V1, same, just conductor short circuit it is. That is just a small line wire it is. So this is also V1 only. So no need to apply any nodal analysis. So calculation is simple or not? Yes, that's why we are going to approximate circuit. Calculation will become easiest compared to previous diagram. So this is the first approximate circuit. We use this circuit in OC test. Remember, in open circuit test, we will use this first approximate circuit. Now, this R0 X0 we call, this is we call no load branch, also called shunt branch it is. No load or shunt branch. And this R01 X01 is there, no, combinedly. This is in series with load. This is load. This is no load branch or shunt branch because in parallel with load it is. And this R01 X01 we call load branch it is. R01 X01. Remember this, in test we use this terminology again. This is called load branch R01 X01 because in series with load. And R0 X0 we call no load because no load only we got these terms R0 and X0. Okay. Now below this diagram, write some important observations. Right. Side heading observations. Completed this diagram. Yes, this is approximate, right? Side heading observations. Completed now, all of you. Taken? Observations. Below this diagram, right? Observations. So what are that observations is? This is approximate circuit. Means what are the problems we will get in this figure? Deviations we are getting or what? I naught is not flowing in R1 X1. Okay. Just now previously also I said that I naught is not flowing in R1 X1. So impedance drop will not take place. Means no load impedance drop we are neglecting in this figure. No load impedance drop we are neglecting. So write that first point. In first approximate circuit, neglecting no load impedance drop. No load impedance drop. What is that? I naught into Z1. That is not taking place. Means negligible, neglecting that is. Second, no load copper loss also will not take place because I naught is not flowing in resistance R1 now. So I naught square R1 will not take place. Right. In this circuit, no load copper loss is negligible. No load copper loss is negligible. Okay, next one more. As I naught is not flowing in that R1 X1 means leakage flux also neglected. No? Due to leakage flux, we have I naught X1 drop, reactance drop. But now I naught is not flowing in R1 X1, particularly X1, means that leakage flux also neglected in this first approximate circuit. Right. No load leakage flux. That is what? No load leakage flux. Under no load, there is a leakage flux on primary that is very small. Now that is negligible. No load leakage flux. No load leakage flux on primary is neglected. On primary is neglected. Negligible. Okay. So these are some deviations or observations from first approximate circuit. See, all these points important only in engineering services conventional examinations. Maybe in gate point of view, you may get very less chance to ask the question, the deviations from first approximate circuit, second approximate circuit. You don't get question on this first approximate, second approximate. But these circuit you have to use in OC and SC test, and you will get question on OC and SC test. So each and every point, every link you should know to solve the respective questions. If you see the conventional questions, particularly engineering services conventional question, one question will cover mostly half of the transformer. One question only, it will cover half of the transformer. They will give a question on efficiency, for example. To find that efficiency, they will give OC data, short circuit data. You have to utilize that OC data, short circuit data. Using that, you need to find efficiency. Means mostly half of the transformer they will cover in only one question. Okay, so don't neglect any point. Right. First approximation we have seen. First approximate circuit. Now second approximate circuit. So after this we take break. Second approximate circuit. Now what we do in second approximation is observe. This is our first approximate circuit now. This is our first approximate circuit. Now what we do in this is, still we will go with one more approximation. That is, we will neglect the no load branch completely. No load current we neglect, because what is the value of no load current compared to load current? Small, 5%. So let us neglect that no load current. Then if you neglect no load current, neglecting no load current means what? Zero. That means completely remove this R naught X naught here. Then only this load we have R01 X01. That's it. No load current is negligible. When you neglect that, still the circuit is very easy. Very easily we can solve the current I1, whatever we need to calculate. Very easy. That is our second approximate circuit right here. In this circuit, neglecting See, when I mu zero, don't say that flux is zero in the core, no EMF, or nothing will happen in transformer. So don't get this type of doubts, because this is our calculation purpose. We are neglecting the small values. That means that there is no flux, there is no nothing will happen in transformer. Don't think like this. Okay, it is there. Flux. So drawing the circuit, I naught is zero. Therefore, we have only R01 and X01. This is load. This is our second approximate circuit. Supply voltage. Now, whenever I naught is negligible, I1 equal to I1 dash itself. R01, X01, and load. That's it. So this circuit we use. This circuit we use in short circuit test, particularly. Why in short circuit test is, short circuit means what? Load is shorted. If load is short, the current flowing is very high or not? Yes. Now, with respect to this short circuit current, if you consider no load current also here, there is ISC in this short circuit current, very high. Compared to short circuit current, what is no load current? Very less. So we can remove that no load branch. That's why we are removing that no load branch here. Okay. So this is the second approximate circuit. No load branch completely eliminated in this. So this is our second approximation. We use this is in short circuit test, remember. Okay. So with this, equivalent circuit part is completed. So remember the circuits so that we can utilize in some other topics. Now after break, we will start losses in transformer. Losses. So in the losses, the most important one is iron loss. So I can say this year, that is in 2022 also, we can expect one question from iron loss, either for 1 mark or 2 marks. Very important, guarantee. And if you take any competitive examination, engineering services, without iron loss, mostly 99% there will be no paper. Particularly competitive examination, 100% there will be a question on iron loss. Okay, so take a break. After break, we start losses. Let's see one question before losses. Read the question. If an ideal transformer has inductive load element at port 2, so this is secondary side load impedance or load element given as inductance only. The equivalent inductance at port 1 means if this inductance is transferred to primary side, what is the value? Inductance or resistance, same formula. What is that? If you transfer a resistance or inductive reactance or inductance also, what is the formula? If you transfer from secondary to primary, divide with k square. Okay, right here. Therefore, the inductance refer to primary, refer to primary. So port 1 means primary side here, port 2 secondary, refer to primary, equal to, so already the inductance is L divided by k square, divide with k square. If you transfer any value from secondary to primary, resistor or reactor, anything, divide with k square. Now what is the k first? Given here n is to 1 is the turns ratio, n is to 1. Now what is the transformation ratio? Transformation ratio 1 by n. Turns ratio n is to 1. Transformation reciprocal of that 1 by n. So k is 1 by n. Substitute here. So L by 1 by n square. And this is n square into L. So option B is correct. Okay. That leakage flux drop only we are compensating with this inductive reactance drop now. So in two way you can understand that. That is due to leakage flux some voltage drop, or due to leakage flux whatever EMF induced EX1, that is compensated by this inductive reactance drop. Okay. Next. Completed. Right side heading, losses in transformer. Now whatever we will see losses in transformer, same for induction motor also, or any other machine like AC machine, synchronous machine also almost same. The only additional loss in that you will get is mechanical loss. Mechanical because it is a stationary static device, but in the rotating machines, the additional loss will be mechanical loss. Okay. See that. Mainly the losses in transformer are first copper loss, also called ohmic loss, also called variable loss. Variable loss. N square omega L. No, because they given only L here. So with respect to L, we are calculating. Otherwise, if they ask XL, then XL equal to omega L. But they are not asking complete reactance. They are asking only inductance. XL proportional to L only, no? So however, we write XL by K square, L by K square. Okay, with respect to L only they are asking. First is copper loss or ohmic loss or variable loss. And second one, iron loss, also called core loss, also called constant loss of transformer. Constant loss of transformer. And these two are the main losses. Our major losses are only these two. Okay. These two only major, or in every calculation we will see only these two losses, copper loss and iron loss. And third, there are some minor losses. This is common in every machine. They are stray load loss, stray load loss. And one more is dielectric loss, dielectric loss. So these two are major losses. In every numerical, we will consider only these two. And briefly, we will see about these minor losses also here. But we never take this is in our calculations. Only these two we take. Stray load loss and dielectric loss. Dielectric loss, where this loss will take place. Dielectric, related with insulating materials. No, it will take place in insulating material. Insulating materials, this dielectric loss will take place. And copper loss in the winding, copper wires, and iron loss in core, transformer core, and stray load loss. So this is stray, means other than this copper and iron, whatever the parts of the machine we have, like if you see the transformer tank, we have transformer tank that is made up of iron only, no? So in that also there is a small loss. So these are all comes under stray losses. So that we will see again briefly once. Windage loss we don't get here. This is not rotating machine, no? Okay, let's see first copper loss of transformer. Friction and windage loss. That's why I'm saying mechanical loss is not there here. What is mechanical loss? Additionally, this will be there in other rotating machine. Mechanical loss. So mechanical loss is uh, friction and windage loss we call. Mechanical loss or friction and windage loss. This is mechanical loss. Okay, we don't have this loss in transformers, only in rotating machines. Where is the hysteresis loss? Means iron loss is the sum of two losses, no? Hysteresis and eddy current. So wait for some time. Let's see first copper loss. First one, copper loss or variable loss of transformer. Copper loss. Now this loss is due to what? Resistance of windings. Copper loss or variable loss. This is mainly due to resistance of windings. It is due to resistance of windings. Resistance of windings. Okay, so whenever there is a current in the winding, it will cause an I square R loss called ohmic loss or copper loss of transformer. Now considering due to primary resistance, what is the total copper loss in transformer? Tell me first. Total copper loss due to primary winding R1, due to secondary winding R2. Primary side, what is the copper loss? I1 square R1. And secondary winding, what is the copper loss? I2 square R2. Okay. Now sum of these two is the total copper loss in transformer. Suppose how to find this I1 and I2 first in transformers. R1, R2 already we have seen. We can find R1, R2 values by conducting Kelvin's double bridge test, resistance measurement, that is. Now how to find this I1, I2 of transformer? See, on every nameplate of transformer or in every numerical, mostly in calculation of this, you will have the rating of transformer. Rating, let some power rating 10 kVA and some voltage rating 400 volts by 200 volt, two winding transformer they will give. Then how to find the currents in the respective primary and secondary? This is E1 by E2. How to find current on primary side? Whatever the current we are calculating, these currents we call full load current, means rated current, means up to this much it can supply. So what is that? I1 FL, full load current. I1 equal to, how to find current rating? KVA is there, voltage rating is there. Now KVA or volt ampere by voltage. will give current. So 10 kVA, 10 into 10 cube divided by primary side 400. Calculate this, you will get 25 amperes. Okay, 25 amps. This is the primary full load current. Similarly, if you want secondary full load current, how to find that secondary full load current? Same volt ampere, because I said already in definition, transformer volt ampere is same on both sides. Same volt ampere on both sides. So 10 into 10 cube, and secondary voltage is 200. Now what it means? What is this value? Calculate 50 amps we get. This is the secondary full load current, and this is primary full load current. So these currents we have to find and substitute here. You will get total copper loss. Let's some 1000 watts you got. Now the same total copper loss you can also find by other way. What is that? With suppose you don't know the I2 value. You don't know I2 value. You know only I1 value. Then how to find total copper loss? Yes, you can find. How? Transfer that secondary resistance to primary side. Then what is the total copper loss referred to primary? I1 square R0 1. Can we find like this or not? Yes. I1 only I know. Total resistance I transfer to primary. Then what is the total resistance? R01. So I1 square R01. Or we know only secondary current but not primary current. Then how to find? Transfer total resistance to secondary side. I2 square R02. So all these values are same. Whatever you will get in the first equation, sum of these two. Second also you will get same answer. Third also you will get same answer if you calculate. So all are same for same values only. Anything you can calculate. Okay. This is nothing but full load copper loss of transformer. Full load copper loss of transformer. Any equation you can utilize full load copper loss. I2 square R02. Anything you can take, either I1 square R01 or I2 square R02. Okay. Now, if it is required to find copper loss at half full load, how to find that? How to find that? So this is copper loss at full load right here. Copper loss at full load. This is the formula. I2 square R02 or I1 square R01. Anyone. Suppose I am following I2 square R02 now. Now, what is the copper loss at half full load? Next, copper loss at half full load. Half full load means which one will become half here? Current only. See, load variation means current variation only we take, not voltage, because voltage is fixed always. Voltage rating will never change. If load is changing means current is changing. So half full load means what is the full load current I2? 50. Then what is the half full load? 25 ampere. What is the 3/4 full load? Calculate that 3/4. 25 plus 12.5. 37.5 is the 3/4 full load current. So like that, whenever you get questions like half full load or 70% full load or 80% full load, current variation it is. Okay. Now I am writing here copper loss at half full load. Copper loss at half full load. So in the same equation, I will take in place of I2 half. Now I2 by 2 whole square. Resistance never change. Whatever the load, resistance is fixed. R02. Okay. Now if you find it is 1 by 4 I2 square R02. Now what is I2 square R02 means? Just now we calculated I2 square R02 means full load copper loss. Okay. Now in place of that, I am writing 1 by 4 into full load copper loss. Therefore, copper loss at any fraction of load. Copper loss at any fraction of load is at any fraction of load x. At any fraction of load x. X is fraction, maybe 50%, 70%, 80%, anything. X is copper loss at any fraction x full load. is equal to, how can we write general formula? See, 1 by 2 means 1 by 4. 1 by 4 times of full load copper loss. Copper loss at half full load is 1 by 4 times of full load copper loss. Then what is the copper loss at x full load? X square into full load copper loss. X square into full load copper loss. So this is the way to find copper loss at different fraction of load. So we will see one example so that you will understand clearly again. So for that we call it is variable loss. Why we call it is variable loss? Observe this. From this equation, copper loss is proportional to what? Square of current, no? Resistance of winding fixed. It never change. It is proportional to current. This current in the windings is variable current and it depends on load of transformer. Whenever load increase, current increase, or whenever load decrease, current decrease. So simultaneously this loss I square R value will change. That's why the copper loss is a variable loss, because load on transformer is variable, the loss also variable. Okay, this is a variable loss which depends on current. Variable loss which depends on current. Copper loss at half full load is 1 by 4 times of full load copper loss. So numerical you will understand 1 by 4 times of full load copper loss. Not it is half. Generally we think copper loss at half full load means if full load copper loss is 100, half full load will be 50. No, this is 1 by 4 because it is proportional to current, square of current. Copper loss proportional to square of current. Remember this. Next. We have one more in the copper loss is per unit copper loss. Per unit copper loss. However, we have previously seen per unit resistance drop or per unit reactance drop. In the same way, per unit copper loss. So the formula for this per unit copper loss is, it is also same, actual value by base value. Per unit copper loss is nothing but full load copper loss by the power rating of transformer. Base means rating of transformer. So the formula for this, right, first per unit copper loss, right, it is the ratio of full load copper loss. It is the ratio of full load copper loss to the volt ampere rating of transformer. It is the ratio of full load copper loss to the volt ampere rating of transformer. So what is the full load copper loss divided by volt ampere rating of transformer? So copper loss in watts, and people will get doubt here is, so this copper loss is in watts and here you are giving volt ampere. So both are not having same units. Per unit value means both numerator and denominator should be in same units. But we are not taking here. We are taking how it is volt ampere rating. Per unit copper loss, this is due to resistive element. Actually, take active power. At the denominator, power in watts should be there. Watts. What is watts? VI cos phi. Okay, VI cos phi. Power, active power means VI cos phi. Apparent power means volt ampere. But for resistive case, what is the power factor? 1. Then even if you write watts, only VI you will get. You don't get that cos phi. Cos phi is 1 anyhow. because resistive case. Due to that, at the denominator, we will take directly whatever the rating of transformer is there in the question, volt ampere rating. Directly we substitute. Clear? Why we are not writing watts there? Volt ampere rating only we take. Now, what is the copper loss? I1 square R01 divided by copper loss. You can take anything, I2 square R02 or I1 square R01. Anyone you can follow. So I'm writing I1 square R01 divided by volt ampere rating. Primary voltage E1, primary current I1. As we are writing primary, write primary current, primary voltage. Or if you write I2 square R02, this is also correct. Anything you can take. Divided by, because both are same values, E2 I2. Anything you can write. Okay. Now I'm following this first one here. Observe what happened. One important relation you will get. That is I1 gets cancelled in this. Okay, I1 gets cancelled. And what is left finally? I1 R01 by E1. Now what is this? Tell me. IR, nothing but voltage drop. IR is what? Voltage drop divided by voltage. What is the term we call? Just now we written previously. Per unit resistance drop of transformer. IR by E is what? Per unit resistance drop or per unit resistance of transformer simply. So this is per unit resistance drop of transformer. Okay. So what is important definition here? The per unit copper loss of transformer is nothing but per unit resistance of transformer. If in any question, if you see that per unit resistance, there is a copper loss also in the question. Okay, mainly in efficiency calculation, losses required for us. So they don't give copper loss directly, but they will give either per unit resistance or percentage resistance, anyone. That means that copper loss is given. Okay, for that you should know this point. Never forget this, important. Or percentage copper loss. Per unit percentage, no different, just multiply with 100 equal to percentage resistance of transformer. Okay, so you will see one example, you will understand very clearly for this. Remember this equation. So what is the full per unit copper loss? Full load copper loss by volt ampere rating of transformer. Write one question. Taken up to this. Write the question. Right. A 10 kVA transformer. A 10 kVA transformer has percentage resistance equal to 2% and percentage reactance equal to 5%. Calculate copper loss of transformer at half full load. So try this. Tell what is the answer you will get. Copper loss of transformer at half full load. How much? First try it, whether right or wrong, just try it. You should reach at least, whether right or wrong. What is the copper loss at half full load? Yes. Sanjay, right. 50 watts. Yes, good. Most of you right. 50. Correct. 50 watts is right. 50 watts is right because uh, to find copper loss at half full load, first we need what is the copper loss at full load condition. Then we can find it any fraction. Okay. Now, given that percentage R is 2%, percentage R is there means copper loss is there in the question. Then we know percentage copper loss of transformer is nothing but percentage resistance of transformer. Both are same. What is the formula for this? Full load copper loss divided by volt ampere rating of transformer, as it is percentage no into 100. Otherwise, in per unit copper loss, if you write, don't take this 100. Now, what is the percentage R given? 2%. 2. This is equal to full load copper loss divided by rating. This is the volt ampere rating of transformer. Volt ampere means don't substitute 10 here. In volt ampere, you have to write 10K. So 10 into 10 cube into 100. So full load copper loss is how much from this? Full load copper loss 200 watts you will get. Okay, this is full load copper loss. Always remember from this percentage copper loss or percentage resistance, you will get full load copper loss only. This equation is valid for full load copper loss only. Okay, now we have the formula copper loss at any fraction x full load. What is the formula? X square into full load copper loss. Now we need copper loss at half. Copper loss at half full load. X square is 1 by 2 whole square 1 by 4 into 200. This is 50 watts. So like this we need to find copper loss at any fraction. Anything for 70%, suppose they given. What is copper loss at 70%? 70% means x equal to 0.7. Now substitute here 0.7 whole square into 200, whatever you get. Or what is the copper loss at 80%? Means x equal to 0.8. 0.8 whole square into full load copper loss. So like this. Okay, next one more question. Try to solve one more question. Completed. Right, one more. Write the question. A 20 kVA transformer, a 20 kVA transformer has a copper loss of 200 watt 200 watt at 1/4 full load. Copper loss of 200 watt at 1/4 full load. At 1/4 full load. Calculate the percentage resistance of transformer. Calculate the percentage resistance of transformer. Try this. So previously given percentage R, you calculated copper loss. Now in this question, reverse. Copper loss is given. Now you need to find what is the percentage resistance of transformer. Opposite to previous question it is. Opposite to previous question. What is the answer? Yes. Yes, right. Yes. So what is percentage or of transformer? Nothing but percentage copper loss only, no? Percentage resistance, nothing but percentage copper loss. What is the formula for percentage copper loss? Full load copper loss by volt ampere rating into 100. But in the question, there is a copper loss of 200 watts This is at 1/4 full load. This is not at full load condition. So first you need to calculate what is the full load copper loss. Okay, given copper loss at 1/4 full load is 200. Then what is the copper loss at full load condition? How to find copper loss at full load? You can use the same previous equation, or one more way is what we know, copper loss proportional to square of current. Full load means 1. 1/4 full load means that 1/4. So it is proportional to square of current. So I can write directly 1 square by 1/4 whole square into 200. Copper loss at full load. Okay, or 1 by x square into full load copper loss, same as the previous this equation. This equation you can utilize. Okay, then how much it is? 16 into 200. 16 into 200, 3200 watts. Now substitute here, 3200 divided by volt ampere rating is 20k, 20 into 10 cube into 100. So it will be 16 percentage. The percentage resistance of transformer is 16 percentage. Okay, so you can find percentage, or if they given copper loss, or if they given percentage, or you can find copper loss at different loads. Okay, with this copper loss complete, next we start iron loss. So completed now, this always all everyone. Iron loss is very important, not only now, because iron loss is not one topic to just listen and leave. It will come in entirely, mostly in every up to completion of transformers completely, like efficiency calculation or voltage regulation calculation, or in three-phase transformers again this iron loss topic continuously will come, like hysteresis, eddy current calculation, all. So this hysteresis and eddy current losses completely depends on equations. We have some mathematical equations, based on that only we get numericals. Particularly in OC test, open circuit test, we will calculate iron loss of transformer. So there, if you have good idea about these losses, there you can easily find the iron loss, sum of hysteresis and eddy current loss. Okay, so second, iron loss of transformer. Iron loss, also called core loss, also called constant loss it is. So why it is constant, at the last we will see, that is at the end of this iron loss we will see why it is called constant loss. Iron loss or core loss. So this is indicated by Wi, which is the sum of two losses. One is hysteresis loss and eddy current loss. So it is a combination of two losses. One is hysteresis loss. Let WH, and second eddy current loss. Eddy current loss. Let it is WE. Hysteresis and eddy current loss. Completed. So first we see hysteresis loss, and then eddy current loss, and finally again we come to iron loss, sum of these two losses. Okay, right. First one, hysteresis loss of transformer. Right. First one, hysteresis loss of transformer. Hysteresis loss. hysteresis loss. Now, what is this hysteresis loss? Many people will say one word directly. Due to reversal of magnetization, it will take place. Yes, this is right only. But what it actually means? Now here I will show you the BH curve is non-linear. Why it is non-linear? I will show you here. So don't leave up to the end. I will show you the most important graph why BH curve is non-linear in this last one. So mostly today hysteresis loss only will complete, and by tomorrow only we have to see eddy current loss. Maybe by tomorrow we don't have class. Maybe Sunday I think. Sunday we will see the remaining. Okay. Today we see hysteresis loss only. See, this is due to reversal of magnetization. What is meaning of this? What is the nature of flux flowing in transformer core? Alternating. The nature of flux is what? Alternating, no? Positive half, negative half, positive half, and so on. So due to this, for every 10 millisecond, because our frequency 50 hertz, so time period is 20 millisecond. So for half cycle time period, 10 millisecond. For every 10 millisecond, the flux is changing the direction, positive, negative, and so on. Due to this, that is called reversal of magnetization. Due to this, we are getting this hysteresis loss. Now see what is actually happening, why we call it is loss. Observe. Considering one cycle of flux, alternating nature of flux. So one cycle I am taking, for example. Okay, this is flux varying with respect to time. Now let it is 0, 0 degrees, 90 degrees, 180 degrees, 270, 360. One cycle. So to complete one cycle, 360 degrees now it is. So 0 to 180 degrees, the flux is positive, and 180 to 360 negative. And again in that same half cycle, there is a variation of flux. 0 to 90 degrees. What is the nature of flux? 0 to 90 degrees, flux increasing, and reaches maximum at 90 degrees. This process of flux we call magnetization process. See, magnetization means whenever flux increasing, that is we call magnetizing process. Whenever flux decrease, that is we call demagnetization process. Now what happened? Magnetize, because flux increases. From 90 to 180, what is the nature of flux? Decrease. And 0 at 180 degree. This is we call demagnetize. Flux decreasing, that is we call demagnetize. Again, from 180 to 270, what happened? Flux increasing, but in reverse direction, and maximum at 270 degree. Now, this is also magnetization only, no? Yes, this is also magnetization, but in reverse direction it is. Next, 270 to 360 degrees. What is the nature of flux? Decreasing to 0. This is we call demagnetization. Only one cycle we are considering, and we will apply in the material what happened it is. Okay. Now, this nature of flux flowing in core or magnetic material. Now, if you consider silicon steel, that is we are using now material for transformer core. If you consider a small piece of silicon steel, ferromagnetic material it is. See, in these magnetic materials, we have dipoles. Dipoles. How many dipoles? Can we count these dipoles? No. Some lakhs of dipoles will be there in small piece of material also. Dipole. Why we call dipole? Because suppose there is a magnet, permanent magnet is there. This is north, south. If you break it is into two parts, it will act as two magnets or not? Yes. And if you break it is into 100 parts, it will act as 100 magnets or not? Yes. So like that, if you break any number of parts, two dipoles definitely exist. Dipoles, two poles, north and south, poles will exist. Like that, if you consider a magnetic material, we have number of dipoles in this. So these dipoles we indicate like this with a arrow. Arrow indicates that flux direction. What is the flux direction in a magnet always? If it is north south, what is the direction of flux in the magnet? south to north internally, and externally north to south. This is the flux direction. So this internal arrow indicates this dipole indication, that is. So this type of dipoles, lakhs of dipoles will be there. We cannot count, we cannot see also. This is one dipole. See. And this is one dipole. So for example, just I am taking some 4 dipoles. Okay, some 4 dipoles I taken just to show it is. So each one is called dipole here. Dipole. This is also called domains. Dipole or domains. Okay, dipoles are domains. So if you observe this microscopic picture of this magnetic material, the dipoles are domains are present randomly. Randomly means is all in one direction? No. This is whenever no flux is passing in the material. This is the position of dipoles. Okay. When there is no flux means you did not given any supply to transformer. At that time, is any flux is there in the core? No flux. At that instant, this is the position of dipoles. Is any dipole having, are all the dipoles is in any one direction? No. One is upward, one is downward, like this. Randomly they are present. There is no any orientation for this. But now what happened? Check. Let us allow the flux. Suppose flux is entering or passing in the material. Now we will observe for each quarter half, that is 0 to 90 degrees, what happened. So let us consider first 0 to 90 degrees. What happens? Observe here. So 0 to 90 degrees. What is the nature of increasing? Suppose flux is entered into the material. Flux passing now. If it is 0 to 90 degree position, flux is increasing due to that magnetization process. These dipoles slowly align in one direction. All these dipoles slowly align in one direction. Now, this is the position of dipoles exactly at 90 degrees. See, when flux is 0, this is the position, first one, randomly present. But slowly, whenever flux increasing, step by step magnitude increasing, exactly at 90 degrees maximum flux, at that instant, this is the position of dipoles. All dipoles are in one direction. All dipoles align in one direction because of magnetization in that direction. Now, this is at 90 degree. Okay, this is at 90 degrees. Next, 90 to 180 degrees. Listen carefully here. 90 to 180 degrees now. Now, what happens from 90 to 180? Flux in the material, magnitude of flux decreasing. That is called demagnetization process. Now, during that, what happens to these dipoles? Observe. Now, these dipoles, whenever flux is increasing, all try to align. Now, whenever flux is decreasing or force is decreasing, now all dipoles will come back to the random position slowly. All dipoles will come back to random position slowly. Random position. This is the position exactly at 180 degrees. Why? At 180 degree, what is flux? 0. If there is no flux, there is no force acting on the dipoles. So they are randomly present. Randomly they are present. Okay. This is at 180 degrees exactly. Next. 180 to 270 degrees. 180 to 270. Now you may guess easily what happened. So what is the nature of flux from 180 to 270? Observe the figure. Flux increasing, but in the reverse direction, flux increasing. So whatever 90-degree position dipoles in one orientation, opposite to that orientation will be there, like this. All dipoles will try to align in one direction, which is exactly opposite to 90 degrees. This is the position exactly at 270 degrees. Maximum flux negative. That's why it is exactly opposite to 90. Okay. Next, again remaining 270 to 360 degrees. 270 to 360. Now what happened? From 270 to 360, what is the nature of flux? Decreasing, decreasing. At 360-degree, flux is 0. Flux is 0. Due to that, again, exactly at 360, as flux is 0, all dipoles will attain a random position like this. Like this, the dipoles will change. This is for one cycle only. This is for only one cycle. Now, what is our frequency? 50 hertz. Means 50 cycles per second. Means in 1 second, in one cycle, one time orientation change. Like that, in 50 cycles per second means 50 times the dipoles are changing the direction like this, quickly, very, very quickly. 1 second, one time. 50 cycles per second means 50 times it will change the orientation or direction of dipoles. This is at 90-degree, this is at 270, this is at 90, 270, and so on, continuously 50 times in 1 second. So during this orientation from one direction to other direction, these dipoles will consume a small amount of power. These dipoles will consume a small power from supply. So they will consume because freely they don't rotate now. Why they are rotating? Why the dipoles are rotating from one direction to other? Because of the force is there inside, magnetizing force changing, positive, negative, positive, negative. Due to that reason, the dipoles are changing. So during the change in the orientation or direction, these dipoles are consuming a small amount of power. Now, that is loss for us, but that is useful for the dipoles. That is loss for us, but useful for dipoles. That's why we consider this is a power loss. And this is called as hysteresis loss. Power loss or hysteresis loss we call. Now tell me, if the nature of flux in any core is DC, constant flux, is there hysteresis loss? No. If the nature of flux is DC, what is the hysteresis loss in the material? 0. Why 0? Because of DC, positive. Always same direction of flux, no change in the flux. Then all dipoles will align one direction and fix, and they don't interchange again. Then as they are not interchanging, they don't consume any power. Fixed, always in same position. Orientation is fixed. They don't change again. Continuously, if you observe for long time also, dipole's direction will be same. So due to this reason, if the nature of flux is DC in any material, the hysteresis loss 0. Not only hysteresis, eddy current loss also 0. Why? How eddy currents will form? If flux is changing, no, then only eddy current will produce. Otherwise, if flux constant, no eddy current, so no loss. So totally iron loss is 0 if the nature of flux is DC in any iron material. This is there only in the stator of DC machine. Stator of DC machine, 0 iron loss. No iron loss in stator of DC machine because their flux is DC. And due to this reason, when we need to laminate any core, when we are laminating any core, when there is eddy current loss, we are laminating to reduce that. But if there is no eddy current loss, is it required to laminate? Not required. That's why stator of DC machine is not laminated. That is a solid core. Stator of DC machine is not laminated. Remaining every part of machine will be laminated. If you take induction motors or synchronous machine or DC machine armature rotor, that is also laminated. Only stator of DC machine we don't laminate because no eddy current loss. Then why we should laminate unnecessarily? Just cost will increase if you laminate. Okay, remember this. So write the statement of this hysteresis loss. Write statement. Whenever any magnetic material, whenever any magnetic material is subjected to an alternating flux or time varying flux, we call an alternating flux, then the dipoles of the material will interchange. The dipoles of the material will change their orientation for an every half cycle. For an every half cycle. During this, the power consumed by dipoles, the power consumed by dipoles is called as hysteresis power. Hysteresis power are treated as a hysteresis loss. Treated as hysteresis loss. Treated as hysteresis loss it is. Okay. So can you measure this hysteresis loss by keeping any meter? No. So we cannot measure hysteresis loss with any meter. Like power we are measuring in electric circuits by placing watt meter in the network circuit. But here in the core, in the transformer core, we cannot find any meter directly. So you cannot find hysteresis loss directly. So for this, we have one mathematical equation given by one of the scientists. So directly we utilize this equation to calculate hysteresis and eddy current loss, both. Okay. Now, before that, let's see why BH curve is non-linear. I will show you here itself. Observe this. BH. So drawing graph between the magnetic flux density and field intensity. Now, B proportional to always flux. B. What is B? Flux per area only, no? Area never change. Flux only variation. So B proportional to flux. And what is field intensity? MMF. What is MMF? Ampere turn per unit length. That is field intensity is MMF by unit length. So H equal to Ni by L. So in that H proportional to mainly current. Ni by L. N constant, L also constant, only current variation in winding. So H proportional to I. So this axis you can treat as flux and current axis or BH axis. Okay. Now observe. So little concentration required to understand why it is nonlinear. Observe here. When current is zero, what is flux? Zero. When current increase, flux also increase. Current increasing, see this is current axis. When current increase, flux also increase. Now 0 to 90 degrees it is. This is 0, 90 degrees. 0 to 90, what is the nature of flux? Increasing. So this is magnetization process. 0 to 90 degrees, flux increasing, maximum it reaches here, suppose. Okay. Current increases, flux also increases. Now, whenever current decrease, flux also should decrease or not? Yes. So little concentration required. See, this is our current signal, magnetizing current, I mu. And flux also in phase with this, no? Yes, flux also in phase with this. Whenever current is increasing, flux also increase. Whenever current decreasing, flux also decrease. Whenever current zero, flux also zero. Like that, when current increasing in reverse direction, flux also increasing in reverse direction. So remember this. This is current. This is flux. Okay, both in phase. This is our electrical representation electrically, but we are applying these signals to magnetic material now. So little concentration, observe. 0 to 90 degrees. Now from 90 to 180, current 90 to 180, current decreasing to 0. So at 180 degree current is what? 0. So this is first current increases maximum. Whenever current is maximum, flux also maximum. Flux also maximum. Now current decreasing. Whenever current is decreasing, flux also decreasing, 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 decreasing. Whenever current 0, actually flux should be 0 in the core, but the flux will not be 0. There will be a small amount of flux here. See, current decreasing, current decreasing. So flux also decreasing, but flux is not following exactly the current relation, because whenever current 0, flux has to be 0, but it is not 0 here. This is not 0. Signal is 0, but flux, whatever BH curve we are drawing, this BH curve is with respect to material we are drawing, magnetic material, or with respect to core we are drawing. So little concentration required. You people definitely will get doubts how it is not becoming 0 here. See, current 0, actually flux signal is 0. Flux signal is 0 only, but flux in the material is not 0. That flux now we called, what is this flux we call? This is we call residual flux. This is we call residual flux. This is called residual flux. There will be a small amount of flux in the material, even the current is 0. Even the current is 0, there will be a small amount of flux in the material, because in materials, flux, ferromagnetic materials particularly, even current is 0, flux immediately will not be 0. So now I will show you the best example, electromagnet. Observe. Take a electromagnet. Now I'm giving a DC supply. Supply is given to this. Now current will flow. So whenever there is a supply, current is flowing. So this is the current. When there is a current, there is a flux. So applying right hand thumb rule, flux is produced like this. Okay, this is flux. Flux is there. Okay, now flux is there. It is acting as a magnet. Suddenly now I will remove this supply. I will remove the supply. Tell me, there is the flux in the magnet is now 0, or it will be there little bit. It will be there, no? Yes. Totally flux is not 0. There is a small amount of flux still for some time. For some time, that flux we call residual flux. This is the same thing happening in transformer core also. Current is 0. See, current is 0, no? Current axis it is 0 here. But flux in the core is not 0. There is a small amount of flux still present in the core. That flux we call residual flux. Okay? That flux we call residual flux. Okay? Now, see, now current is becoming negative. Follow the carefully this diagram. Now slowly current is negative. Current negative means what is the flux newly produced? Actually flux produced opposite. No, if previously flux positive here, observe here positive flux. When current is 0, still there is some positive flux. But whenever current negative, flux direction also actually whatever flux is produced, that flux is in reverse direction. Now that flux and this positive flux gets compensated slowly. Now the flux in the material slowly come back to 0. Now it will be 0 at one of the current, at one of the negative current, the flux in the material is 0. This current, or this is we call coercive force. This is we call coercive force. This is from here to here. This is we treat as coercive force. What is coercive force? It is the force. H means what? MMF only, no? Magnetomotive force it is, or proportional to current. It is the force or current required to bring that residual flux in the core to 0. Here residual flux, here flux in the core is slowly 0 now. Now that current or that force we call coercive force. So what is coercive force? It is the force required to bring the residual flux in the material to zero. That force we call coercive force. From now what happened? Now flux in the core zero, no? Yes, zero. Now what happened? Check. If current still is negative, current is still negative. Now the flux in the core increase in reverse direction, increasing. Now current increases up to some maximum value, negative, and flux also reaches maximum. Now again, one cycle completed. First increasing, that is one half is completed. First increase and then decrease. First one cycle is completed. This is 0, 90 degrees. Again 180 degrees. Now 270 degrees. Now 270 to 360. Now again current is decreasing to 0. So flux also decreases. But even current is 0, flux will not become 0. Same thing, residual flux it is. Now after a small positive current again, now flux will become 0. This is also same coercive force. Whatever length is there left side, same length on right side also, coercive force. From now again current increases, flux increase. So like this it will follow. So this is the BH curve or hysteresis curve, or we call BH loop it is. Now 0, 90 degrees, 180 degrees, 270, 360. Now from now again next cycles will continue, next cycles from here, like this, and so on. Now same loop will continue in this way, magnetization, demagnetization, and so on. Same will continue now. Okay, this is called BH curve or BH loop or hysteresis curve. Okay, this is a non-linear. Now tell me why it is non-linear. Why BH curve is non-linear? Because the magnetization and demagnetization, this is magnetization and this is what, demagnetization, both are not in phase. Magnetization and demagnetization are not in phase, they are deviated. This is due to mainly some coercive force. This is due to the presence of residual flux. What is the property to have residual flux for the material? The property is called retentivity. Due to retentivity of material, retent means hold. Even current is 0, actual flux to be 0, but in the material it will hold some flux. That flux we call residual flux. Okay, so listen one more time this BH curve. See, initially current 0, flux also 0. Now current increase, flux also increases, current increasing, flux also increasing, and reaches maximum at 90 degrees it is. This is at 90 degrees. From 90 to 180, current decreasing. See, current decreasing. Now at 180 degrees exactly, current 0. So flux also decreasing, but at 180 degree current 0, but flux is not becoming 0. This is due to the property of retentivity, which is having some residual flux in that. So due to that, even current is 0, flux is not 0. Okay, now current is becoming negative. From 0, current is becoming negative. Whenever current negative, a reverse flux is produced. That reverse flux will make that residual flux slowly to become 0. At one of the current in negative direction, the residual flux totally becomes 0. That current or that force we call coercive force. So what is coercive force? So if you want to write that definition also, it is the force required to bring the residual flux, or to make the residual flux, or to bring the residual flux to 0. It is the force required to bring the residual flux to 0. Here it is 0. From now, whenever current is negative increasing, whenever current is negatively increasing further, then flux increases in the reverse direction. Flux increases in reverse direction. And when current again decreasing to 0, flux also decreases, and same thing again repeats. Residual flux, even current is 0, flux is not immediately 0. Again after a small positive current, now the flux will reaches to 0. Same, due to coercive force. That is called coercive force. Again, when current increases positively, flux also increases. Now same phenomenon will repeat for the next cycles. Okay. Now clear now all of you why it is non-linear. Yes. Yes. Residual flux is due to the property of material, that is a property we call retentivity of the material, because we are using ferromagnetic material. So in these materials, even if you remove supply or current is zero, flux in the core will not be zero immediately. For some duration, based on the material strength, up to some duration, the small amount of flux will be there in material. That flux we call residual flux. Check from your side itself, because nobody getting problem, that is. Don't confuse. At 180-degree current and flux is zero. What is this? This is electrically. But what we are drawing, this is the figure we are drawing for iron material we are drawing. In the material, what is the variation with respect to current we are drawing? Okay. This is the signal with respect to electrical, but this is the figure we are drawing for magnetic material. In the material, how the flux variation with current. Retentivity is what? Retentivity means it is the ability to hold flux in the material. It is the ability of material. It is the ability of material to hold some flux, to hold some flux. Okay. So this is we call BH loop. BH loop are also called hysteresis loop or hysteresis curve. Hysteresis loop, name of this graph. Or magnetization curve also we call magnetization. Okay, let's see now how to find hysteresis loss. See, retentivity is the property. Residual flux is what? A small amount of flux present. Why it is present? Due to retentivity. As the material having some retentivity property, it is having some flux. That flux we call residual flux. Okay. Due to retentivity only, residual flux will be there. Clear? Now see how to find this hysteresis loss. Right. This hysteresis loss we can find by two methods. One is the graphical method, one is mathematical method. Graphical method means now we have drawn a graph here, BH graph, BH loop. If you are able to find this area of hysteresis loop, this area, whatever area we got, if you able to find this area of hysteresis loop, that means the area of hysteresis loop will give hysteresis loss for one cycle. This is for one cycle we drawn. And for next cycle, what happened? Same loop will overlap. Same loop will overlap. That's it. So if you able to find this area, that is the hysteresis loss for one cycle. Then what is total hysteresis loss? Just multiply with frequency, whatever we apply. Okay. So right here 1 point. The hysteresis loss can be calculated by The hysteresis loss can be calculated by first method, graphical method, and second, mathematical method. But in this, important is mathematical method only. So using that only we get questions. Mathematical method. Okay, right. First, graphical method briefly. How to find graphically? Graphical method. Write this right here. So graphical method means draw the BH curve for the given material. So transformer core, silicon steel, no. So with respect to that material, draw the BH curve. Okay, draw the BH curve or hysteresis loop or curve. Then calculate the area of that hysteresis loop. Okay, right here. Hysteresis loss for one cycle. Hysteresis loss for one cycle at hysteresis loss for one cycle equal to area of hysteresis loop, area of that hysteresis loop. But is it easy to find that area of hysteresis loop? Observe, what is the shape of that hysteresis loop? Non-linear shape. So we need to integrate this from limits that we should have in the graph, and integrating and calculating the total area occupied by that hysteresis loop. If you able to find that area, then we can find hysteresis loss, but it is difficult because it is not a standard shape, no, like circle or square or rectangle. We can find areas easily, but for non-linear waveforms or non-linear graphs, we need proper integration for this. So it is difficult. So if you are able to find, then it is the procedure. Hysteresis loss for one cycle is area of hysteresis loop. Therefore, total hysteresis loss, total hysteresis loss, WH equal to area of hysteresis loop, area of hysteresis loop multiply with the supply frequency. You will get total hysteresis loss. Okay, whatever the frequency you are giving, that frequency you multiply, you will get total hysteresis loss. This is the method in graphical approach. But mostly we have this mathematical method only. From here only we get questions. Right now, mathematical method. Mathematical method. Second, mathematical method. Mathematical method. See, in this method, we have one equation. So this is given by scientist. So directly we take this equation. These two equations you should remember. One is hysteresis and eddy current loss. Two equations. Okay, right here. In this method, hysteresis loss can be calculated. Hysteresis loss can be calculated by using an empirical equation. By using an empirical equation. Empirical means derived. So directly we take this equation, empirical equation, that is WH equal to eta B max power x into VF. So never forget this equation. So this is given by the scientist named Steinmetz. Scientist Steinmetz. Okay, Steinmetz. And here this eta we called Steinmetz coefficient. Steinmetz coefficient. And B max, you know, maximum flux density it is. Maximum flux density. and x is Steinmetz coefficient, Steinmetz exponent, Steinmetz exponent, and the value of this x is 1.6. This is for silicon steel, silicon or CrGO steel, anything x equal to 1.6. So whether it is mentioned or not, x is always 1.6 only we take, because which material we are using? Silicon steel. So for silicon steel, it is the highest value is 1.6 only, and for remaining cast steel, cast iron, x will reduce, like 1.5, 1.4 will be there. So x is 1.6 for silicon steel, and where V is volume of core, volume of core. If volume increase, definitely hysteresis loss increase, because when volume increase, dipoles increase, and more dipoles, more power consumption. So that is more loss for us. And frequency, F is frequency. Okay. And in one of the examination I have seen, if the coercive force of magnetic material increases, what is the hysteresis loss? If the coercive force of a magnetic material increase, then what is the hysteresis loss? What is the hysteresis loss? Yes, increase. Yes, right. Increases. Increases. Yes, good. Because observe here. If area increase, loss increase. If hysteresis loop is thinner, loss is less. If area is less, or means thinner loop. If BH loop is thin, definitely hysteresis loss is less. If it is wider, hysteresis loss increase. If width of the loop increase, hysteresis loss increase. If height of the loop increase, then also hysteresis loss increase. Or if coercive force increase. See, this is coercive force. This is coercive force. If this is increases, means width will increase automatically. If width increases, then automatically area of the loop increase. So hysteresis loss also increase. Okay. So remember this. So here still we have some two cases, case one, case two. So tomorrow we continue this. Not tomorrow. Tomorrow we don't have class. I think Sunday we have class again. Okay. Sunday we have class, and for timing mostly it is 2 to 9 will be there, and you also check in your portal once. Okay. Sunday. Okay. 2 to 9 means 2 to 8 or 8:30 mostly we take. Okay. Okay.
Hello, sir.
Tell me, Prajit.
So, good evening, sir. Sir, slide number 26.
26.
Sir, actually, my net was disconnected at that time. Can you re-explain this?
This one.
Kelvin's field windings of this, the right hand side
This
part.
is just I given regarding resistance, different resistance we have, no?
Yes,
Low
sir.
resistance, medium resistance, high resistance. Low means less than 1, medium is less than 1K, high means greater than 1K.
Okay.
Okay, in measurements you will get this is just I given brief information. And how to find the resistance? Low resistance, which method is best? Kelvin's double bridge is best for low resistance.
Okay, okay, sir.
For medium resistance, what is the example for low resistance first? All transformer windings and armature windings less
Okay.
than 1 ohm. Medium resistance example is field windings.
Yes, sir.
100 ohm, 200 ohms will be there.
Yes.
For field winding or medium resistance calculation, which method is best? These two methods, Wheatstone and volt ammeter method.
Okay, sir.
And for high resistance,
Yes, sir.
example is insulating material, and methods are Megger and LOC, loss of charge.
Okay, okay. Thank you so much, sir.
Okay.
Good evening, sir.
Tell me.
Sir, in 35F,
Uh,
Sir, here E1 is induced EMF process, so its flux is opposite to main flux.
E1.
35, sorry, 34, I guess. Yes, sir, this one. Here, E1 is due to induced induced
E1 is due to
flux.
main flux.
Ah.
5. EX1 is due to leakage flux.
Sir, E1 is induced, no, sir.
E1 induced and EX1 also induced. This is induced due to what? Additional this leakage flux, no? See, let us consider due to the current I1 here, primary current, total 100 flux lines produced. In that 100 flux line, 90 lines are in the core. They are circulating in core. Due to that 90 lines, the EMF induced on primary is E1, and due to that secondary side EMF induced is E2. And due to the 10 lines, where is the 10 lines here? Rotating primary side, here itself. In through air, it is completing their part. Now that due to that 10 lines, whatever EMF induced, additionally will induce in the winding, no? Okay.
Sir, how it is plus and it is like it should be minus, no, sir. It is leakage.
So okay, don't neglect that plus here. Just I shown. Remove that plus also. Remove this. So due to main flux, EMF induced is E1. Okay. And due to leakage flux, additional EMF induced is EX1. Now to compensate this induced EMF, we are considering additional inductive reactance drop in the winding here, I1, X1, on both primary and secondary side.
That means it can be E1 minus EX1 also.
E1 minus, because this is due to total flux, whatever EMF induced on primary, total flux is addition only now. Total 100 lines, total EMF will be let 100 volts. Okay. In that 90 lines only present in the core material, iron material, and due to that 90 volts is induced. And where is the 10 lines here? 10 lines are circulating through air. Now here itself it is flowing in the primary winding only. And that 10 lines also will cause an EMF in the winding or not?
Sir, but E1 is induced in the sense its flux is opposite to main flux, no, sir. So it is opposite to main flux, and this leakage is in the direction of main flux. So they should be
Leakage,
minus.
okay, no, leakage flux direction we cannot draw directly. Just we represented now here. Leakage flux direction, how can we find?
It is, however, from main flux, no, sir. Then it should be in the direction of main.
No. Okay, no need of that much thinking regarding this leakage flux. So due to leakage flux, some EMF will drop or not? Just tell me.
Yes.
Not only here, if you take any generator also, for example, we have alternator. In the alternator rotor, we give field winding, some flux will produce. And in the stator, we place winding, RYB, 3 phases. Whatever flux produced in the rotor, north pole, south pole, if whatever flux produced, if it reaches to the stator, then total EMF induced. Suppose 100 flux lines produces here. The total 100 flux lines will not go to stator. 90 lines only will touch with stator. And 10 lines rotate here itself. Now, how much EMF will induce in the stator? Regarding that 90 lines only EMF induced, no, in the stator.
Yes.
90 lines are going
10
there.
will waste.
10 is waste. Means some voltage reduced or not?
The reduced means it should be minus.
Reduce. So see clearly 90 volts induced. Suppose if there is no leakage flux, how much voltage will induce there?
100.
100. But as some flux is leakage, it is okay. You are considering like that. If it is total 100, now okay, you think okay, right only. According to you, it is right. Okay. Any more?
So this should be E1 minus EX1, sir.
Yes. Any other?
And in the hysteresis curve in first quadrant, all three points are at the same point, sir.
Like
Or this
one?
ending point is
ending
Or
point
is little far away from that.
it is little far away because
Okay.
already there is some current here now that is
Oh.
making residual flux 0. Then to have the same maximum flux, it will take little more current. Okay,
Okay.
little
Thank
far
you.
away. Hmm. Jitender,
Hello.
tell me Jitender.
Sir, in the first slide, the question you solved today in the beginning,
Slide number
1,
25, I think. Tell me here.
yes, sir. Here you said that we have to neglect the
Iron loss.
iron loss. Sir, but if we are considering I naught directly, if we are not using this, I tried to solve by
Okay, like that also okay, right only.
which, sir?
You are considering directly flux, no?
Yes, sir. I'm considering
Flux equal to Li.
MMF by reluctance.
That is also okay. MMF by reluctance. Okay.
Yes, sir. And then MMF is N into I naught. And then
Actually, MMF is due to N into I mu, not Ni naught. There also.
it will not be, if sir, if complete is I naught, then will not take N into I naught.
Actually, here no load current same means when no load current is same, if flux in the core is same, no? Simply. If flux is same, I mu same. If flux is constant, IW also same.
No, sir, I'm saying if no load current is I naught and the part, okay, so only I mu component we have to
Yes,
take.
yes, yes. Simple.
Okay, sir.
Anyway, that is also same you will get.
Yes, sir. I'm getting same, but I thought I was doing something wrong, so that's why I
Okay.
thought to ask.
Okay, right, good.
So I mu I should take there only.
Yes.
Okay, sir. Thank you, sir.
Hello, good evening, good morning, good evening, sir.
Tell me. Rakesh.
Sir, can you once exact equivalent circuit slide, sir?
Slide number.
Circuit.
Number is
Actually, I forgot. Previous to this, sir.
next. Okay. Exact equivalent
Exact. Yes,
circuit.
sir.
This
Yes,
one.
sir. Yes, sir. Sir, my doubt is here, like, you are
Uh,
taking R2 primary side as R2 dash and X2
uh,
as X2 dash and load as
uh.
X2 dash. But why we are not taking I2, sir?
I1. What is I2? K times of I1 dash. No, I1
Yes, sir.
dash equal to
K1.
KI2. No. Then what is
Yes, sir.
I2? I1 dash by K. So
I1.
if you transfer I2 to primary side, what it will become? KI2. You have to multiply current
K.
with K and you have to divide voltage with K.
Yes, sir.
V2 dash we divided no, by K. V2 by K. Current is
Yes, sir.
reversed no with respect to K. That's why just multiplying KI2. This is KI2.
So
I2 only
I1 dash
KI2 here.
is here like
Both equal. I1
okay.
dash equal to K8.
I2 dash.
Okay.
Sir, but I1 dash generally like in the yesterday's discussion we consider that as a flux which it is a current which is used to reduce the flux, no sir, to maintain constant flux.
Yes, yes. To compensate
Now
secondary
this
flux.
yes sir. So sir, my doubt is like I1 dash is equals to I2 dash, sir. Correct, sir?
No, I1 dash is K times I2. No, not exactly equal to I2. So in the
I2 dash,
last
sir. I2
yesterday's
dash.
class in load operation, I2 dash equal to KI2.
Yes, sir.
I2 is transferring to primary, no? Then I2 dash
Yes.
was KI2. That KI2 is
Okay.
nothing but here I1 dash. Both are same.
Okay, sir.
Okay.
Okay, sir. Sir, and next sir, in copper losses.
Mm.
Sir, yes, sir. In this, like, can you tell why you put a cross mark to I2 load, I2 full load, sir?
I2?
I2 full load, why you put a cross mark there? Bottom, sir. Yes, sir.
Maybe at that time I may say some statement because of the why I forgot why I placed.
We can consider no, sir. I2 full load also.
Anything you can calculate, but for some reason I said it is.
Okay.
Okay. Okay.
Okay. Thank you, sir.
Okay. Jayashree,
Sir, good evening, sir.
tell me.
Sir, in 40F, sir.
40F.
Yes, sir.
Tell me.
Sir, here, no load leakage flux on primary is neglected, the third point, sir. But in the circuit, we have drawn I naught, no, sir. For the
How?
first point, I naught is not flowing through R naught and X naught. So
Not
it
R0, R1, X1.
oh yes, sir. R1 X1 it is not flowing. So we are saying that no load impedance is
Not
negligible.
taking place.
Yeah, neglected. Then the third point, but current is flowing, no, sir. I naught current is there in the circuit, no, sir. How no load leakage flux is neglected, sir, on primary?
So, okay, you are considering no load. Actually, due to leakage flux only, we are considering I naught X1.
Oh,
Okay.
Sir,
Due to leakage flux only, we have considered reactance drops.
Okay, sir.
Then I naught X1 is not taking place means corresponding leakage flux also not taking place. No, means we need to neglect that. Neglecting that corresponding leakage, no load leakage flux.
Then we no need to draw that no load branch, no, sir, shunt branch.
See here, I naught is flowing in R naught X naught. This is there, but it is not flowing in R1 X1.
Yes, sir.
As it is not flowing in R1 X1, that's why we neglected whatever the corresponding deviations we are getting, we neglected here. So that is not flowing in only R1 X1, no, but it is flowing. I naught is there, but for our calculation purpose, we neglected because that is not flowing in R1 X1 branch.
Okay, sir. So that is clearing the first point only, sir. Only, no,
Clear,
sir.
but no need to write third also, because if it is asked particularly about leakage flux, then you can consider. Otherwise, not required this point. Because already here we neglected I naught X1 means leakage flux neglected in that itself.
Yes, sir. For simplicity only, no, sir. But actually, there will be there, no, sir.
Yes, correct only.
Yes, sir. Sir, then in the 48F, sir. Sir, yes, sir. In this, the copper loss in full load, you have written 1 square by 1 by 4 square, no, sir?
This is formula only. What is the formula of copper loss at full load? Reverse 1 by x square into copper loss at fraction of load. 1 by x square. So I written directly because if you don't know formula also now, directly also you can use like this. See, copper loss proportional to square of current. Copper loss proportional to square of current. So they given copper loss at, suppose with respect to current I am calculating, given copper loss at a current of 10 amperes is 100 watts, for example. Now they are asking what is the copper loss at a current of 7 ampere. Then how to find this? Simple. How copper loss at 7 required, we have copper loss at 10. Then what is the formula of square of current? 7 square by 10 square. Then what is the copper loss at 7 means 100 into 7 square by 10 square. So same, full load means 1 square.
Okay, sir. Yeah, there x we considered as 1, sir.
Yes, 1 by 4. X equal to 1. Full load means.
Yes, sir. For full load, x equal to 1. So 1 by 4 we have taken.
Yes,
for,
yes.
Okay, sir.
Next, Vaishnavi.
Sir, in 37F, sir.
30?
7F.
Oh.
Sir.
This one?
This one, sir. I didn't listen, sir. Here, why did you write ideal transformer?
Because in this dotted line, inside this dotted line, we don't have any resistor, any reactance, nothing. Okay. What is resistance in anything for ideal case? 0. So this dotted line includes only ideal transformer. So if you take completely, that is practical case, because we have resistance, reactance, leakage flux, everything. And one more dotted line we drawn here. This,
yes, sir.
2 parallel lines we have drawn.
2
no?
lines.
You should not
Oh,
draw
yes.
if you take complete figure. Only for dotted line you can draw these 2 lines.
ఓకే సార్. ఇప్పుడు మామూలుగా రెసిస్టర్ ఉన్నప్పుడు దానికి 2 లాసెస్ ఉంటాయి కదా సార్, ఎనర్జీ లాస్ ప్లస్ వోల్టేజ్ డ్రాప్.
Voltage drop and copper loss.
కాపర్ లాస్ అంటే హీట్ వల్ల
yes.
వస్తుంది సార్. మళ్ళీ వోల్టేజ్ డ్రాప్ ఎందువల్ల వస్తుంది సార్?
Generally voltage drop, IR drop kada, just whenever current is flowing through any resistive branch, some voltage will drop there. Just KVL. Network KVL apply చేస్తాం కదా, కరెంట్ అండ్ రెసిస్టెన్స్ ఉంటే సమ్ డ్రాప్ కన్సిడర్ చేస్తాం. దాంట్లో హీట్ ఏం ఉండదు, జస్ట్ వోల్టేజ్ డ్రాప్ గా రిప్రజెంట్ చేస్తాం. దట్స్ ఇట్.
అంటే వోల్టేజ్ వేస్టేజ్ లాగా.
Just like that. Some voltage will reduce.
Sir, in 50 F, sir.
Tell me.
సార్ ఇక్కడ మామూలుగా జనరల్ గా ఇప్పుడు వోల్టేజ్ V1 అనేది Vm sin omega t కదా సార్. అప్పుడు కరెంట్ అనేది 90 degrees లాగ్ అయినప్పుడు ఇక్కడ ఫ్లక్స్ కూడా 90 degrees లాగ్ అంటే మామూలుగా 90 degrees నుంచి స్టార్ట్ అవ్వాలి కదా సార్. కానీ ఇక్కడ 0 degrees నుంచి స్టార్ట్
This
అవుతుంది.
is our reference. మనం ఎక్కడైనా స్టార్ట్ చేయొచ్చు కదా, assumption. Just that's it. Otherwise, if it is flux now, where is the voltage? Voltage will be here. Voltage ఇక్కడ ఉంది -90 దగ్గర. ఎక్కడైనా ఉండొచ్చు.
మళ్ళీ డైపోల్ అంటే ఓకే సార్.
Magnetic materials లో డైపోల్స్ ఉంటాయి కదా. Magnetic materials లో if you break a magnet into several parts, each part again will act as a magnet. So దాన్ని డైపోల్ అంటాం. Dipole means 2 poles. Every part of every piece again will act as a magnet. దీంట్లో lakhs of dipoles ఉంటాయి magnetic materials లో. ఇవన్నీ అర్థం అవ్వాలంటే మీరు మ్యాగ్నెటిక్ మెటీరియల్స్ అగైన్ క్లియర్ గా చదవాలి ఒకసారి.
Hello, sir.
Anil, tell me.
Yes, sir. Sir, I have a doubt on yesterday, sir.
Can tell me that?
When two conductors carrying current, we will going to say, and that can be applied on the transformer, sir.
Yes.
Can you please explain that once again?
Page number గుర్తుందా?
No, sir. I don't.
That is in the last class.
Yes, sir. Yes.
If 2 conductors carry current in opposite direction, then what is the force acting between the 2 conductors? Repulsive. No? Okay.
Okay.
If 2 windings, so manam we are placing 2 windings on same limb, no?
Okay,
LV HV both. No? So in the diagram, LV HV we are placing on the same limb. So LV carrying current one direction, let cross dot. Then what is HV current? Opposite. To satisfy Lenz law, it is because flux produced by 2 windings always opposite direction. Okay, due to this.
Yes.
Now, if 2 windings carry current in opposite direction, adjacent to each other, opposite direction. Now, what is the force between these 2 windings? Repulsive force.
Repulsion force.
Due to that repulsive force, which winding will try to dislocate? Which winding trying to go away from the core? Whatever outer winding, what is the winding? HV. So that winding will try to dislocate. So that is we call repulsive forces.
Okay, sir. When repulsion and a condition manaki emana avutadi sir effect?
Under normal steady state operation, no problem. Only under transient, like sudden disturbance in winding currents, suddenly Generally, the MMF of LV, MMF of HV balanced. MMF,
Okay,
both
sir.
same, the flux produced almost equal on them. So
Yes,
both
sir.
balanced, so no problem. But during some abnormal conditions, some MMF of these two will not balance. One is very high, one is small. Then if it is very high, then repulsive force may create some damage to windings. Only under abnormal operation.
Okay, sir.
Okay.
Sir, I have another doubt.
Hmm.
Sir, at the generating station, how many generators we carry to generate the power?
That depends on capacity of generating plant. Now, some generating stations may have 2 plants or 1 plant or 5 plants. That depends on their capacity, availability of area they will place. It is not fixed like having 1 or 2 only. Any number they may have.
Okay.
Okay.
Okay, sir. Thank you, sir.
Hello, sir.
Tell me, Nilesh, Ramesh.
Sir, hello.
Wait.
Hello?
Ramesh, tell me. Ramesh, tell me.
Sir, it's Nilesh, sir.
Nilesh, tell me.
Sir, at 37F, sir.
You are from which place?
37F.
Tell me.
Sir, exact equivalent circuits now.
Slide number?
37, sir.
Okay.
Sir, why we can't place I0 before R1, sir? You are explaining. I didn't get it, sir.
Oh, if you draw
the
before
shunt
R1
circuit.
X1, if you draw before R1 X1, I0 will not flow in R1 X1. Okay.
Okay, sir.
But actually, whenever I0 is flowing, due to that, there is some copper loss in the winding or not? Means I0 square
Yes, sir.
R1 will takes place or not? Takes place. And whenever there is a current I0, there is some voltage drop in the winding or not? Yes, that is also there. So when it will take place? Only if you draw after R1 X1. But if you draw here, I0 will not go here. R1 X1 में I0 नहीं जाएगा ना?
Okay, sir. I get it. Thank you, sir. Hello, sir. I have a doubt from express class. If a load get a lead power factor, I consider like for a angle of 135 degree, there is a theta for a 130 degree I1 dash. The power factor like theta, if I increase the theta 2 in the leading direction, theta 1 is also increasing. If the load is more leading or less leading, the theta 1 keeps on increasing. I don't understand how it attacks like this.
No, how much
It's
you
like
taken? How much you taken power factor? Cos theta 2 equal
to load angle theta 2 135. 135.
That is wrong, no? Actually,
if I tried it with 95
no.
and if I tried it with 175, both 95 and 175 make theta 1 increase.
No, theta 2 is 1035 wrong, because power factor angle you have to take between 0 to 90 degrees only.
I just said in the second quadrant, so I told like the I1 dash.
No.
In opposite direction.
Maybe you send your figure, I will check in Telegram. Send your diagram. Huh?
Okay.
Hello, sir.
Gangadhar.
Page number 50, sir.
50. Tell me.
Sir, in case of DC, you said that the iron losses are 0, no, sir?
Yes.
Sir, how, sir? Once again, please explain, sir.
Because totally iron loss, nothing but hysteresis eddy current. Hysteresis loss depends on variation of flux. No? Whenever flux changes positive, negative, then dipoles also changing. During that, they are consuming power. But if flux is DC, is the dipoles will change?
No, sir.
No, then there is no power consumption.
Sir, regarding eddy current losses, during DC also the field will be present, no, sir?
field is present but not varying. No, according to Faraday's law, when EMF will come? Only when variation is there.
No, sir.
Stator,
If current is present, no, sir. According to right hand thumb rule, when EMF is some field is present, around
what
the
is
current is.
what is that field? What is that field? Constant. No?
Yes, sir. Constant.
When stator, suppose this is stator, what is the flux passing in the constant magnitude? So it is not varying. Whenever conductor is stationary, flux also stationary. First, is EMF will induce?
No, sir.
Then how currents will flow at that time? No current, no eddy current, no eddy current loss.
Okay, okay.
Good evening, sir. Hello, sir.
Saran, tell me.
Sir, in yesterday's class, you gave an example of giving excitation to 100 volt side and 200 volt side. That I did not understand, sir. How to take that 100 volt side and.
Okay, you only mistake that is confusion, no? See, what is that question? 200 by 100 volts, no?
200 by 100 volts, sir.
What is the meaning of that 200 by 100? First, try to understand. Then you will get. That is, you make that volt. So there is a transformer. One winding is 200, other winding is 100. So they
Yes,
given like E1 by E2. So in this case, you can change your primary, secondary or not. Suppose I want 100 is my primary. Okay, according to the date nameplate, it is primary E1, it is secondary. But I will change that same transformer. I will give 100 volts as primary, 200 volts is secondary. I will consider, I will give source here. And I will connect load to this. Anywhere you can use transformer. Okay, or directly also you are using, suppose. What it means, the voltage rating. If you 200 on primary means you need to give supply voltage 200. Okay. If you apply 200 volts supply voltage, how much voltage you will get on secondary? 100 volts you will get on secondary. Or same 200 volts side, suppose you given 100 volts, how much voltage you will get on secondary?
200.
50 volts only.
50 volts, 50 volts.
Like that you take from secondary side now. Suppose secondary 100 volts side I given 100. Then how much voltage I will get on other side? 200.
200.
See, I taken LV as my primary now.
Okay, sir.
Okay, if I given 100, 200 you will get. Suppose same 100 volt side, I will apply 50. Then how much voltage you will get on other side? 100 volts you will get.
100 volts.
Like that.
Sorry, you gave an example of like frequency, no, sir, 40 hertz and 60 hertz like that.
So there also 200 volt, 50 hertz initial. 200 volt, 50 hertz. Then how much voltage you will get on secondary? 100 volts you will get. Okay. Suppose same 200 volts side, I am applying only 100 volts. Only 100 volts.
Okay, sir.
At the same time, I am reducing frequency also. V1 by F is constant, 25 hertz. Then how much voltage you will get on secondary? 50 volts. Okay. Because
so
V1 by F we are keeping constant here.
Okay, sir. Okay, sir.
Okay, then we get 50 volts here. Otherwise, if you keep 100 and this is 50, what is the flux density? If it is 50, what is flux density? Decrease. When flux density decrease, what is the flux in the core also? Decreasing. Then your secondary voltage is not 50, less than that you will get.
Okay, sir. Okay, sir.
Still any doubt?
Sir, that 80 volts also same like this only, sir. 80 volts.
Oh, yes. That 80 volts we applied on other side. If you apply 80 volts on other side, how much voltage you will get on this side? 160 you will get.
Okay, sir. Sir, here you told V by F is equals to constant. No, sir. Here 200 by 50 means 4. Okay, sir. Okay, sir.
100 by 25 you have to apply.
Okay, sir.
Okay.
Hello, sir.
Shivaji. Shiva.
Sir, good evening, sir. Sir,
Page number
33 F, sir. Sir, here how that EX1 becomes a loss. So you explained with respect to that rotating machine. So I understood that, sir. So if we apply the same analog here, then EX1 will be the voltage that is supposed to be induced in the secondary winding, right, sir?
Yes, not secondary, in primary, wherever leakage flux, there it has to be induced.
Sir, but here you said
Observe. This E1, E2 are balanced each other or not? Because E1, E2 is due to same flux.
Yes,
okay,
sir.
but EX1 and EX2 are not balanced each other. Why? EX1 is due to phi L1.
Yes, sir.
EX2 is due to phi L2. Is leakage flux on both sides are same?
No, sir.
No, different, no, that is.
Yes, sir.
So EX1, EX2 will not get balanced each other, but E1, E2 balanced because they are compensating in the magnetic core. But phi L1, phi L2 are not balanced because they are in the air. They are not compensating. So EX1 is different, EX2 is different. So to cancel out that EX1 and EX2 in the respective winding, we are assuming inductive reactance drop in both primary and secondary side.
Then how it becomes a loss, sir?
Loss means drop, some voltage drop. Actually, if total flux is there within the core, our E1 will increase, no?
Yes, sir.
Then some flux is leakage, no? Now what means that some voltage drop in the winding or not? EMF induced, actual EMF induced is drop.
Okay, sir.
That is loss for us.
Okay, so with respect to that rotating machine, you said that
yes,
we will be giving supply to the
there
field
you
winding.
can understand easily, but not here.
Yes, sir. Here it is.
Okay, understand.
So with respect to that analogy, we are giving supply to field winding, and some EMF will be induced in the stator.
Yes.
So actually 100 lines you said, and only 90 flux lines will reach the stator winding.
And accordingly, EMF will induce in generator, and some voltage drop there. That is reactance drop.
Okay, sir.
We call synchronous reactance drop in alternators.
Okay, sir. So and if we apply the same analog here, then that voltage drop due to the 10 lines will be a loss, no, sir?
Loss.
Okay, sir. Sir, and then one.
Who is this?
No, sir. And one more doubt, sir. The copper loss is only due to the resistance in the winding, right, sir?
Yes.
Okay, sir. That's it, sir.
Copper loss only in windings, and eddy current loss in core. That is also current, but that current is not in copper. That is in iron.
Okay, sir. Sir, and then the kVA rating will be given in some of the problems. Is it the apparent power or active
apparent
power?
Only. Apparent only. Volt ampere is apparent power only.
Okay,
active
sir.
power means they will give in watts.
Okay. So in case of the copper loss, since we consider only the resistive component and the power factor is 1, so we neglected that.
Yes.
I mean, we consider it as active, right, sir?
Yes.
Yeah. Okay, sir. That's it, sir. Thank you.
Gangadhar.
Sir, in page number 52, sir, BH curve.
Page number
52, sir. Sir, why the BH curve initially is not in linear cohesion, sir? The flux density and the field intensity both are directly proportional to current, no, sir?
Why both are not linear?
No, sir. Initial middle line, no, sir. While it is magnetizing, why it is not linear, sir?
Because of saturation. Saturation it is. Ideal case, no saturation, then it is straight line. But practically, whenever current increase, after a particular value of current, the core will saturate. No, saturate means what? Flux is almost constant. From there, we will take back.
Means initially, still some current, it is linear, no, sir. Then onwards, it starts.
Yes.
Okay, sir. Thank you, sir.
Hello, sir. Hello.
Siddhartha, tell me.
Sir, in yesterday's class, in last problem, sir, why you have not included that imaginary part, sir? I didn't get it.
Because there we need to find power factor.
Yes, sir.
Power factor is cosine term or sine term?
Cosine, sir. Yeah.
That's why only real parts is taken. That is enough to solve power factor.
If by taking imaginary part, the answer will not change, sir.
That is, you may get sine theta. Again, you have to find cos theta from that. You can do that. Is also
Okay,
sine
sir.
theta you will get, theta you will get. Then again cos theta you have to apply that.
Just
Because power
to
factor required.
okay, sir. Just we neglected that.
Yes.
Oh, okay.
Generally, in complex calculation, what we do, equating real parts, equating imaginary parts.
Yes.
To solve any equation, same thing.
Okay. Thank you.
Sir,
Tell me.
the copper loss of offload.
Copper loss?
Of offload ఉంది కదా సార్,
Ah.
దాంట్లో డెరివేషన్ లో కాపర్ లాస్ ఆఫ్ ఫుల్ లోడ్ ఎట్లా రాస్తారు సార్, నాకు అది అర్థం కాలేదు.
Page number? ఇదేనా?
Yes sir, the WCU copper loss of H load is equals to I2 by 2 whole square ఉంది కదా సార్, ఇంటూ R2. అది స్క్వేరింగ్ చేస్తే 1/4 అది వచ్చింది కదా సార్. మరి ఇక్కడ లెఫ్ట్ సైడ్ WCU 1/2 ఫుల్ లోడ్ అని రాశారు సార్, హాఫ్ లోడ్ కదా.
హాఫ్ 1/2 అంటే హాఫ్ ఫుల్ లోడే కదా.
సార్ పైన కిందికి రాశారు కదా సార్, ది సాల్వింగ్.
ఓకే దిస్ ఈస్ కాపర్ లాస్ ఎట్ హాఫ్ ఫుల్ లోడ్. ఓకే అంటే మనం జస్ట్ ఇది ఎఫ్ రాయాల్సింది హెచ్ రాస్తున్నాం అంతే. హాఫ్ ఫుల్ లోడ్ మీనింగ్. ఓకే
సార్, అదే అక్కడ ఫుల్ హాఫ్ లోడ్ రాసి ఇక్కడ ఫుల్ లోడ్ రాసారా, అదే కన్ఫ్యూజ్.
yes.
ఓకే సార్, థాంక్యూ సార్.
ఓకే. అనిల్ కుమార్.
Sir, good evening, sir.
Tell me, Anil Kumar. Tell Anil Kumar. Your voice is not clear.
Sir, can you please explain this problem, sir?
Which one?
46.
Your voice is not audible clearly.
Sir, 46.
46.
Yes, sir.
What is dropped out here?
Sir, problem slide, sir.
This one. This one?
Sir.
Your voice is not clear. You send me in Telegram, I will tell.
Okay, sir. Thank you.
Priyanshi.
Good evening.
Yeah, tell
Good
me.
evening,
Priyanshi.
sir.
Good evening. Tell me.
I wanted to ask about the BH curve. Sir, you said that cohesive force, it is a force which brings residual flux to zero.
Yes.
Then you ask that if cohesive force increases, then what will happen with the hysteresis loss?
Increases, no?
But sir, if the force increases, which brings the flux to zero, so the curve should tend towards zero now.
So okay. You are understanding like if a coercive force is more, quickly it will come to zero. So here this length is coercive force, no? MMF. This length, whatever from 0 to this point, this is we call coercive force or MMF. Or if MMF increase means what? Current increase, no? So you don't think like you are thinking like that. If it is more force, quickly it will comes to zero. But no, not like that. MMF increase means this width will increase or not, like this. This width will be more. After more time, it comes to zero. More MMF required for MMF required is more in order to bring residual flux to zero. Means suppose there is more residual flux, then it will take more coercive force, no? To bring to zero. Then width will increase. If width increases, area will increase. Then automatically loss increases. Okay.
Sir, I also wanted to ask that day by day the portion gets increasing also. So how to revise all of these to keep all those points with time?
First thing is, during this, don't read any new concepts or new points there from different books, because from one textbook to other textbook, the way they explain the concept will change. Okay, so if you read all the books at a time, you will lose entire subject first. The best thing is follow only the class notes first up to completion of total transformer, because in between maybe some concepts are not clear in some other subjects like that, like per units. Maybe some people are aware of per unit and some people are not aware of this. So follow this, and after completion of total transformer, once you try to attempt any previous questions, like particularly engineering services question, objective type. Okay, then you will get some confidence. Then you try to read a standard book, any one book, like PS Bimra is best. PS Bimra is available mostly with everyone. So try to go through PS Bimra. Enough. No need of different books. Only for numericals, you can refer any number of books. But for concept wise, go any one book only. You only asked na previously. Okay. Anybody else? Okay, so I'm closing, and Sunday we meet again. Good night.